Yeah, so I'll talk about neuromorphic, control, neural fields, and symbolic vectors. And it's like a flash talk, right? So I'll a little bit about neuromorphic, and something about control, and something about neural fields. So it's a little bit like flashlights. And the rest we can talk later, or you can read papers. So I would define neuromorphic computing as a brain-inspired computing. And I think thinking about this brain inspiration is what makes it valuable in its own sake. So it's not like whether we have the best computer on earth and the most low-power computer on earth. It's brain-inspired because our brains are awesome, and we, on the way to building these computers, also want to understand the brains. And then we believe that brains do something useful and something unique, so we want to learn from these brains. And it's good to constrain ourselves to really focus on this problem and not just go into any kind of computing. Yeah, so we want to get inspired from the human brain, but also from all those small brains, insect flies, like tiny brains, mid brains. Okay, so what does it mean in terms of computing primitives that we have to use? So the first thing is like neurons. And let's define a little bit what we mean by neurons in neuromorphic computing. So these are some functions that do some kind of integrate, like they sum up input, that's what all neurons are doing, artificial neurons as well. Then they threshold, so there's some non-linearity, threshold. And then they fire. And fire can mean many things, but what is important about this fire aspect is that we have asynchronous computing when it's needed. So when there's information worth passing over, then we pass it over. There's no clock, no continuous sampling. So we have this sparse information going around. And this is the key why our computers are not energy efficient. And energy efficiency is one of our main claims to fame, and also one of the main problems in AI. The second feature of these neuromorphic neurons is that they have internal state. No, biological neurons have internal states because they are physical objects. And in physics, nothing changes like from one moment to the next one. Things have, dynamics, they have some inertia, things change slowly over time. So in our artificial neurons, we also have this internal state as a minimal, and maybe it also has some dynamics. And some examples of these dynamics, maybe there's some leak, so internal state variable maybe just decays over time. Maybe there's some refractory period after firing, it rests for a while. Maybe there's some homeostatic process, so there's some additional dynamics running on this variable. Maybe there's some shunting, maybe there are multiple variables inside that neuron. So these are all the tools that we have as computing primitives in our neurons. Yeah, so we have this temporal computing. Then we might have, some dendrites, so more non-linearities. So the neuron is not just one variable internal state. We can do a little bit more computation within these neurons. Okay, so neurons, and then synapses, connections between neurons. They have weights. In some cases, they might also have some dynamics, call it local plasticity, so the weights can change over time. The weights are the strength of the synapse, right? But in neuromorphic world, we also have delays. So the weights can wait a little bit, and this is a parameter, how much we wait before they transmit information. And then there are some other functions that they can have, like tags. You can tag a weight, so it doesn't change, but this has potential to change. And then some additional signal comes, and then the weight changes. You can have some shunting. So there are a couple more features that we can add, legally add to our neuromorphic toolbox. And this is maybe with neuroscientists, it would be nice to sit down one day and put down what features are there in the neurons and synapses, which might be important for computation. Okay, so these neurons and the synapses is all you have. Maybe not all you need to implement your algorithm. Maybe you need some exponential functions, and if and else, and while and loop. So you don't have it in the neuromorphic world. In the neuromorphic world, to design your algorithm, you only have neurons and synapses.
So, if you're trying to incorporate glia cells and kind of consider the tripartite synapse, would that fit into this definition?
I think yes.
One of these little sub-bullets.
The glia cells is some kind of a neuron. It probably does integrate information in some way. It might don't have a threshold, maybe, as internal state, influences synapses.
Well, it serves as inhibitory neuron. Some glia cells serve as an inhibitory neuron.
The sign, can be positive, can be negative. It's all included here. There may be a couple, as the field develops, right, there might be more primitives. But we kind of have to forget everything else we know from computer science. Even else, at least if we want to try to push forward this neuromorphic brain-like computing framework. Okay, another very provocative statement now, deep learning is something you don't have. Let's imagine you don't have deep learning when you're trying to push forward neuromorphic and brain-like computing. It's a useful tool, and you might use it as you also use normal programming languages with if-else values when you create your neural networks. But no, let's not argue here that this is not something that happens in the brain a priori with this algorithm. So let's pretend we don't have deep learning. And let's pretend that we're interested in closed loop behavior. Because in the end, this is what brains are there for, right? And it's another, like, no, I hope we're all on the same page here. Brains develop to move around. Move around is moving the body around. It's about embodied AI. So why it's so dogmatic? Why do I think it's important when we develop neuromorphic algorithms to follow these rules? Well, because there are all these guys developing all these chips with a huge effort. So they listened to all the neuroscience people and they believed that brain-inspired computing is important, and they see hardware is important for that. So they've invested decades to develop all these brain-inspired chips, and it's not easy to redo them at some point. And these chips, if you take them, they enforce those constraints. So no cheating. You cannot run some exponential function or some if-then loop on one of these processors, like especially those analog ones. So it will enforce these constraints anyway. So you develop your algorithm, you come to neuromorphic people, no, you have to change everything. And it's really nice to do that to avoid this mismatch in hardware algorithm co-design. Because now these guys, they kept left behind. Like algorithmic people have all these nice algorithms, but they're not for us. So what was it for? So we are, as a community, if you want to move this neuromorphic computing forward, we have to kind of work in a coordinated fashion. So no one argues, no deep learning. Okay, that was one flash, neuromorphic. The next one is control. Okay, so as I mentioned to John already, I'm not a control theorist. I never studied control. I studied physics, so that's why I can read the equations and kind of understand what's happening. I think all I know about control, I learned from John's lectures here in Telluride, and those are like, I learned, I think I learned very noisy, but I think I learned enough. And then also Jean-Jacques Slotin's lectures in Capocaccia, but he's also a funny character when he's in Capocaccia, so. Okay, but what I've understood, like what's control about? Like you have a state of your system, which you need to be able to measure somehow, right? That's the first thing, like we need to measure the state, measurement may be noisy and so on. And then we have some desired state where we want the system to be. And we somehow can determine the difference between the two. We can somehow determine the error, something went wrong. So what we want to bring our state closer to the desired state, ideally in the desired state. We can somehow look at the state in the desired state and measure the error. Could be simple difference, could be some other cost function that punishes our state to not be close to the desired state. And there's some feedback going back to the state. Now we change the state somehow so that we minimize this error. Familiar framework, so some people of you might breathe out, because it looks like backprop, right? In backprop, right, you measure the error between the label and the output, and then you change your weight, right, with the variable. So it's basically a little bit like control. Those of you who work on optimization, it's also like optimization, like any optimization problem. That's what you always do. You measure the error, you use the error to change your state, to make it closer to whatever you want to optimize, where you want to be. The difference is that in control, you have to do it very, very quickly, all the time. In deep learning, you do it once, 9 months, and you have your network, and then you use it. And here you have to do this stuff like all the time to keep your system in balance, to keep your system standing, to keep your grid from collapsing. Okay, so now going back to the brain. So the brain obviously does control. What does it control? Like, of course, many things of our internal variables, but in the sense of applications and robotic applications and in the sense of behavior, the most important things that the brain controls is movement. And movement is about placing our limbs somewhere in space, so that's position, or controlling the velocity if we want to track something, or force. And that's it. So we don't need any further directives, but these are the three things that the brain controls. Okay, so when I thought about control, there were a couple more things that come to my mind, apart from just solving this equation and controlling my variable. So what are those? The first thing that comes to my mind are maps. Why maps? Because all those goals, they need to come from somewhere. So I look around and I see objects out there in the environment. I might see a couple that potentially interesting to visit. So I might need to plan and control a sequence of actions. There might be objects with different semantic property. So I might want to control myself differently around them. One is an obstacle, one controller, one is a target, another controller. I want to shake hands, I want to do this. So I might switch my controller to different regimes, depending on stuff around me. So I need to form a map of stuff around me, and I might need to form like sequences of goals. So this is one thing that comes to my mind when I think about control. The other one is reference frames. Because if I have more or less complex body to control, then I start having these different spaces, different reference frame. I have a task space, like this table where I want my hand to be, but then I have the joint space that my brain and me as a roboticist have to control, and then I might have a muscle space. And even if I only think about the task space, there's a space here on this table, but then this table is in the room, and I kind of mentally have to switch between these different reference frames, zoom in, zoom out, anchor different objects. I want to characterize something like relative to Terry, and then maybe like relative to Dylan. So I constantly have to switch between these different reference frames. So the transformations between them is another important thing that comes to my mind. If you think just about the control, then there's this forward and inverse kinematics. And these are the transformation matrices that link the position, for instance, of my end effector relative to the joints. And the Jacobian matrices and the matrices that tell me if I wiggle a little bit, like one joint, what effect does it have on my end effector, and the other way around. It also might remind you training neural networks, right? I wiggle the error, what influence it has on the weights, or if I wiggle the weights, what effect it has on the error. So all these derivatives. Here is something very similar. This Jacobian matrix, but then also transformations about all these spaces, like the retinal space, and then like more eccentric space, like head-centered space when I want to reach for something. I constantly have to switch these reference frames. Then learning is also something that comes to my mind. Why? So if anyone of you have ever done stereo vision, and that was the first thing that I've done as a PhD student, so you put two cameras and you want them to work together. To communicate, and you have to calibrate them. You have to make sure that they know their relative position, and you have to do it every morning, because during the night someone kicked your setup, they shifted a little bit, pixels are really tiny, you have to recalibrate. Now imagine I have a robot, camera here, cameras there, skin sensor, motor sensors, mobile platform. Like I have to do this recalibration regularly, maybe once if everything is super rigid and I've screwed my robot to the table. But if it's a mobile robot that's moving around on some bumpy ground, then it needs to be able to do this calibration almost all the time. Then might need to adapt to changes in its motor plans, or maybe the environment, I shifted the table, I put a different table. So this learning needs to be part of my controller all the time. And then the hierarchy. So, I have a complex system, so I might plan, to make a call on my phone, and then for that I need to first grab my phone. So there's a kind of hierarchy. And some of the controllers in this hierarchy will be continuous, just controlling movement, but some will be discrete. I want to, first reach, then grab, then throw, then catch, go back. So I need these things. So when I think about the controller controlling a robotic system, holistic in the whole thing, and I just develop my controller, does that loop. Now forget about all this stuff, and all this stuff will still need to be taken care of. And then probably someone else will take care of this. So I'll download, some ROS packages for this stuff, but then I lose all my advantages of my neuromorphic controller, like in the first place. And the brain obviously does all of this with neurons and synapses and nothing else. Glia cells, the neurons are more complex, but does all of this. So that's what was driving my research over the last many years. Now I'll show you a couple examples, like of the things related to control that we have built. And a couple means more than two. So brace yourself. And Toby might show me if I talk too quickly. She probably will, but it's recorded. Everyone can see. Velocity control, because I will start with the simplest possible system to control, and that's a vehicle. It's very simple. That's why we already have robots in every home that do that, just controlling the vehicle. Why velocity? Because we started with position. Why don't we control position and go from A to B? Because that's a very unnatural thing for a vehicle. For a vehicle, the natural thing is to control its behavior in its egocentric coordinates. In egocentric coordinates, I can easily control my orientation. That's directly what I control. And then forward speed, two things. And these are the components of a velocity vector, right? Orientation and forward speed. So I want to do velocity control. And it will be reactive control. So no plan. I have this very simple motor plan. My sensor is very close to this motor. So it's kind of a bit implicit control, visual survey. So how does it look like? So can I assume that everyone knows Breitenberg vehicle? That's a Breitenberg vehicle. Doesn't matter if you don't know it. So it's just a vehicle that can turn around and go to goals. So if we kind of want to control the orientation of this robot, then what we need to do is we need to set an attractor in the space of the heading direction of this robot on the direction where the target is, 30 degrees there. So I want to create an attractor there, and then just move forward, and I will arrive there eventually. Then some other mechanism of control that I have arrived there. So in mathematics, if I want to kind of define an attractor, that would be the equation that for the variable phi, which is my heading direction, defines degrees as an attractor. If you look at this, this is like exactly the control thingy, right? So we have a minus phi, that's the error, and our derivative, so the rate of change of phi is proportional to the error. Some of you might also recognize some neuronal equations here. This minus u plus stuff term, right? It all sets attractor for the u. So u will now exponentially kind of relax and approach this a this time. Very kind of fundamental equation, attractor dynamics. Okay, so what we wanted to do is to do something like that on the chip. At that time, they had this beautiful Rolls chip from INI, built by Ming Chao. Ming Chao is the CEO of Sense today. Ning is brilliant, I think, because when I came to Telluride in 2007, Giacomo had his hardware here, these analog chips. They had 8 neurons at that time. So we were building little winner-take-all networks with these 8 neuron chips. And when I joined INI in 2015, they had Rolls chip that had 256 neurons. It's quite a few more. And it has 2 areas of synapses, all like physically instantiated in analog with analog circuits. Normal synapses, just the weights, and plastic synapses, where the weights would change. And that's it. And this is where you have to put, these algorithms on. So how do you do it? So we wanted to have this bright and big vehicle that can both avoid things and go to things. So target acquisition and obstacle avoidance. And these are the architectures. This is how I write down my algorithm. This is my pseudocode. Okay, so we have this little robot, it's called Pushbot. It has a little DVS camera on wheels. So the DVS camera, right, will give us this DVS frame if you want. The events will pop up here. And so we have a very simple heuristics. Anything we see, which is like consistent and there's a lot of events, we want to avoid that. And then anything we see kind of below the midline, because that's the floor, the thing is like down there. So what we'll do, we will just stream all these events to a population of neurons, a vector of neurons. And we will kind of spatially have like retinotopic projection here. Like the events here will go here, and the events there will go there, the events in the middle. Okay, so this is our representation of the visual input. Then we have 2 motor populations. They use different coding, so there are like 100 neurons here. If all 100 of them are active, then we drive like we turn left rigorously. If only 5 of them are active, we turn right a little bit. And then we have the same for this is the right and this is the right population. So they connect to the motor system of this robot and they control the turning. They inhibit each other because you either turn right or turn left. Don't do both. Okay, then we have connections from here to there. They have different strength, meaning that so the neurons here in the middle, they connect to many neurons of these guys. So if I see obstacle in front of my nose, I turn a bit faster. And if I see an obstacle somewhere in the periphery, like I maybe like tend to turn left a little bit. There's like a gradient in the number of connections per neuron here. And the same in the other half of it. Just the same connection. And you can say, yeah, how do you like decide on the strength? Yes, I tune it by hand. And yes, this is something where learning could come into play. But there's this design that I like decide that half of the neurons go to the left, to the right. That kind of makes sense from the symmetry of the task. And then I have this other population that controls the forward speed. I can be faster or slower. I can sometimes make this dependent on whether there are obstacles or not. So I slow down if there's an obstacle. We'll make it dependent on something else in a larger hierarchy, which didn't fit on the Rolls chip with 256 neurons. All right, so then I have this gyro thingy. So if the robot says I'm you, so if it detects, oh, I'm turning, then we know that it gets too many events when it's turning. So we inhibit this visual population a little bit. It still gets events, but less. So we have some kind of saccadic suppression. When you turn, then you just don't let this thing overflow with events. And that's obstacle avoidance. Target acquisition is like almost the same thing. The connections here are reversed. Are they reversed? Yeah. So if my target is, if I'm already almost there, I don't turn so fast, so I don't overshoot. If it's far, then I turn a bit faster. So here it's stronger than in the middle. I have 2 layers here. And I look at the upper part of the visual field because my target is a blinking LED of another robot, and it will be in the upper half. I could have some more intelligent object detection here, also not on Rolls probably. And then I have the second layer that has the winner-take-all connectivity. So it's kind of selective layer. So if I have a lot of stuff happening on the visual field, like here, I will select only one most prominent target because I don't want to have multiple targets and get like chaotic. Right, the rest is the same, and these two populations are exactly the same as these ones, right? They just draw them twice, but these guys, they integrate the input from targets and obstacles and try to do their best. The obstacle, we have stronger inputs. So there's an obstacle, I ignore the target for a while, hopefully come back to it later. Yeah, so we took these two things and now we've written them down not as a pseudocode, but as a real like program. And program for roles looks like this. This is the connectivity matrix on roles. Red ones are inhibitory, I think, synapses, and no, the other one, well, the red ones are positive, blue ones are negative. No, this is the this Winnerty pole population, for instance. There are some positive connections from here to there. These are these weights where we have like one to all connection and one to just a few connection to these motor populations. So I just translate this to this program, send it to the chip, and yeah, let the robot run. And we did like a bunch of experiments, the robot running in the arena, and even in the real world, on the floor, so it will run around and avoid obstacles, with the limitations of this very, very simple perception. This is what happens like in front of the robot in the camera. You can like recognize these obstacle events in lower half, and then other events. These are just events aggregated in some ugly low resolution frames. And this is all that happens on the chip, all 256 neurons, raster plot, right? So that's the population speed, constantly active, turn right, turn left, obstacle on the left, target, memory, right? So this is selective, it's only one. This is what the DVS sees, mass, a lot of mass. Now this gets input to here, IMU left, IMU right, everything that's happening to the chip, that's all that controls of ours. Okay, so that's this very simple.
Is the red object the goal?
In
In your video?
the video, yeah. Let's see. Yeah. That's the goal. Okay.
So how fast can you run it? Because the processing should be fast, no? You run it as a
So as you can see, so the robot is very small, right? So the chip is sitting somewhere on the table and talks to the robot over Wi-Fi, right? But otherwise this runs, in real time. As you know, Rolls chips can slow down to run in real time.
Yeah, but I mean, if you have fast motors, could you just go like a race car?
Especially if I get rid of the Wi-Fi and whatever we had at that time. Okay, so now target acquisition. Target acquisition, like remember, sometimes I might have an obstacle will be stronger, so I will turn away from target. So it would be nice if I could turn back to target again. So this I need to remember where my target was. And remember this DVS population is in the camera reference frame. And the problem is if my camera reference frame is moving, remembering something in this reference frame doesn't make sense because it moved, right? So it maybe was on the left, but now it's on the right. So here already, like we recognize that we need reference frame transformation in order to remember where the target was. So we had an ambition to have this reference frame transformation on our 256 analog neurons. Yeah, so this is the difference, right? So if you don't have memory of the target, you turn away and you never come back to the target, but we want the robot to come back to remember where the target was. Okay, and in order to do that, you have to store your memory in some more allocentric representation. And it's also like true for our eyes, right? We have the retinal representation. It doesn't make sense to store where the target was in this retinal representation. Yeah, so that's a simple thing, right? So that's some north direction. This is the heading direction of the robot. This is where my target is. So this angle is where I perceive the target is the relative to my heading direction. This is where DVS will signal that's where the target is. And my memory should ideally be in some allocentric reference frame, relative to the north where my target was. This information I can use independent on how I turn between memorizing and remembering. Okay, so it's a simple operation that I need to do. I just need to subtract. But remember, I don't have subtraction. I don't have that as my primitive, right? I have neurons and synapses. So how do I do subtraction of two values? So first I don't have values, right? I have to see how do I represent angles, and then how do I do subtraction? And there happens to be an architecture that allows you to do that, right? So if I have some representation of my targets in relative coordinates frames, and I have some representation of my heading direction, which I kind of know, then I can do some magic, and I'll show you what the magic is, transformation map or gain field that allows me to get this absolute target direction. The magic now interpretation looks like this. So this is a little architecture, neural architecture, might remind some people of the binding operation in vector symbolic architecture. Might remind some people of gain fields in eye control, but basically, if I have some representation of my, where the target is on my retina, and some representation of my heading direction, I can combine the two in some kind of two-dimensional sheet of neurons, and then I can read out from the sheet in a certain way along the diagonal. What I get as an answer is like this guy relative to my heading direction, so kind of head direction independent representation. I don't know if that's obvious for everyone. So
The diagonal does the subtract, basically. The fact that you're reading it out along ascending diagonals.
that's what does the subtraction.
Effectively subtracting the mean of their.
No, it's subtracting one. It's like having these two guys and making kind of a convolution, one
Yeah.
relative to the other, and that's like shifting one as if the other one was in the center. And you can also read out along the other diagonal, and it will be like plus. And one diagonal is minus, one diagonal is plus.
Can you somehow also confirm from the vision sensor that what you calculated is right or something like that?
Exactly. Yeah. So,
Yeah.
and then you can build up on that. Not with 256
Yeah.
units. It was already a stretch with 256 units, but that's the architecture. We actually have done it like for 6 neurons. So 6, like our heading was sampled with 6, and then it could fit this architecture. We have-
It's kind of like visual place recognition, just with reference to a single coordinate that's derived from one frame that you've said, yep, that's where we want to be.
Yeah, and then if you go another coordinate, you need another guy like this. Yeah, so this reference frame transformation is very fundamental block. We have worked a lot with it, right? So you get this head-centered coordinates from your kind of eye movements. It's like a steerable map. Like from retinal to head-centered, there's some mapping, right? From retinal to head-centered. But this mapping depends on your eye position. So this eye position kind of changes the mapping. Yeah, that's why it's steerable map. By changing this, you kind of shift your beat around. We have used it in like the largest scope where we've used it in this spatial language architecture, where like we had a lot of experience like that. This robot, it sees some object, and it needs to talk about this object, like where is the red object? It says like, well, relative to the blue thing, it's to the left. Or which object is to the right of the blue thing? It's like, oh, that's the green thing. So it knows colors and knows spatial terms, left, right, above, below. Yeah, so these are the color nodes that I can give the input, or the system can give me output through these nodes. And this is the image, and these are the spatial nodes, left, right, above, below. And again, I can either set the input, what's to the left of something, or the system can answer me, oh, that's to the left of something. These are the colors. So if I say some color, then so the red stuff goes here, the blue stuff goes here, the green stuff goes here. It's like continuous field. I just have 3 slices of that. And if I say blue, then the blue peak will emerge here. And then I have a target field and a reference field. So because where something relative to something will make that object a reference object. So where's their red apple relative to the blue one? So the blue will appear here as a reference object, and the red will appear here as a target object. Then here it's not shown because this is a 4-dimensional transformation matrix, like the one I've shown before. Like this one is 2-dimensional. Here the same thing in 4 dimensions. So it's a combination of this position and this position, and I read out along this 4-dimensional diagonal to get this object-centered field where the reference object is kind of in the middle, and then I can apply like stereotypical representation of leftness, rightness, aboveness, belowness, and then solve this task. So if it runs, so here, like the green object is my target. Where is the green object? Now see the relative. No, which one is to the left of the green object? So the left will be here, and now the blue, like this object appears, and then that's the blue object. So the blue will be as an answer.
Question.
Yeah.
Some of those things are 2D maps and others are something else. Are they all 2D maps? Some look like that.
These are just nodes. These are just kind of nodes. Or you could see this is like a one-dimensional
Activation.
activation, exactly.
The other ones.
The bottom ones are color activation. Yes, thank you. And there's this 4-dimensional thing in the middle. It's just connectivity matrix. Everything else are 2-dimensional. The color is the activation. The red is high. Yeah, and here activation is up. And we've done like tons of. We've there's one paper. Let's see if it shows up. Right, where we've compared these to some psychophysics data, how people like judge and answer to the scenes like that. If the object is not exactly to the left, how they select reference objects, the ones that are closer to your object, the ones that are bigger, more salient, and yeah, we match all kind of psychophysics behaviors.
I still don't understand, so you ask it, go to the
Go to
green
the,
object, left of the red one, how do you do that?
yeah, so that's.
Green object left of the red, what's the?
What's the, so I say, so I tell it, where is the green object? And then the green goes in this field in the end. Like the green is highlighted here and this field is boosted. So the green causes the peak to appear in like green is like this one, right? So it will pop up here. And then it potentially this input goes in both. But by saying where is, so that's marks the target. This will boost this field so that it will form a peak. And this one won't. This just stays as threshold. Although it also gets this input, but it will just be ignored. And then I say relative to the red one. And this relative to will boost this field. So I will boost the red node. It will lead the activation here in the red field. It also goes in both. But first this one now has this peak. It ignores everything anyway. And this one will be boosted. So then I will have to do activation. Now, as you see, there are these discrete events here also. So I boost this thing and I boost this thing, then I again boost this thing and I boost that thing. And this is controlled by a neural state machine runs in the background for this architecture. So when we've done these psychophysics comparisons, we had this kind of neural state machine that parses this input in a very simple way, right? So we just marked relative to is target, where is this target, relative to is reference. And then we have this machinery that parses the scene to drive this architecture and to kind of boost some things and direct the input flow, which is always present, but you kind of highlight different things. And it's like cognitive control within these tasks. We had a slightly different implementation of this architecture where we didn't have to do this orchestration, where it will just emerge just from the flow of information. And there what I could do.
Yulia.
Yeah.
Yeah. Have speed, yeah. So, it sounds like some kind of attentional gaming and so on and so forth, but it seems like, so when you get that key in that field there.
This one?
No,
This
to the left, just backing out to the left there, right? Yeah, in that four-dimensional space where you're doing two-dimensional.
Yeah, two-dimensional.
You get that peak there,
Yes.
which is kind of a multiplication of the two things. How do you implement that in your hardware?
So instead of multiple.
Second part of the question is that's really the core of gaming and attention and all that. It's just the only place where you do this kind of.
No, the core of attention gating is the fact that individual things can get multiple inputs and they have a threshold.
Oh, I see.
So I can have one input that's my attention. And I can also boost it up and down, so it draws attention to this field and not to that field.
I see it.
Boosting. This thing, so I replace multiplication with sum and threshold. And this is what neurons do.
Okay.
So these have to be neurons, unfortunately. There were synapses with some shunting, would be cheaper. But here they have to be neurons. They can maybe sample the space, not obligatory very densely, a bit sparsely with some Gaussian, whatever. Yeah, but they sum a threshold, and that's equivalent to multiplication.
I still don't quite understand why you actually need this field in the first place, because if you're only interested in this one-dimensional projection, like this head center coordinates, like why would you go to the two-dimensional? I mean, you go from two one-dimensional things to a two-dimensional, and then you're projecting back to one dimension. So you could just as well do just a linear combination of the two.
But linear combination is a two-dimensional thing.
Yeah, okay, so it's just a representation of the. But this is
But that's linear. No, it's not linear because of the threshold on the top.
Yeah. So if only one is there, then nothing happens, right?
Okay, but just to be sure, so you actually do have the representation of this two-dimensional, the entire two-dimensional map in the.
That's what you.
In there, yeah.
And that's what makes it so costly, and that's so unfortunate. And that's it would be nice if someone would build the hardware that would do that. And I'm sure the vector symbolic people would also be happy to have some acceleration for this binding thing. Binding is a bit of a costly operation.
But do you then always read it out, like you said, along the diagonal? I mean, was that like, is that literal or was that just a?
This is literal. This is literal. So you sum along the diagonal. Yeah. But there's this paper from Matthew Cook and Deal, right, 2016, where they have shown how you can learn like these readouts out of an architecture like that, right? So here you have your one field, another field, you have this relation, and then you have the output, and you can read them in all directions, by the way. Here as well, like any of them could be input or output. So if I have something, I know where something is on the table, and I know where my eye will be at some point, I can predict where it will land on my retina. So I can use it in all directions. And this is also what Matthew had. And they have shown how you can learn these relations. And they have shown that you can encode any relation, like A plus B, A star B equals C. Like relation between the three things, so not just a function, but the relation. And you can learn it with STDP, any relation. If you have examples, right? Examples you wanted.
Yulia, can I ask you, are you familiar with the work of Edmund Rolls?
Sure.
So he has the spatial view cells that he's been recording from monkeys. It's kind of almost the exact same kind of thing. It's like.
So now the devil's in the detail. Now we use
Sure.
similar ideas and we just we develop these architectures. Like you have some concepts of computer science, how you build programs, and then you write concrete programs and do stuff. So we were writing these concrete programs and do stuff.
He has lots of models about how to do this, like,
Yeah.
you know,
We share the same principles, right? So in my PhD, so I was referring to a lot of his work with sequence learning, for instance.
Okay.
Right. So if you like this stuff, there's a lot of this stuff on this, dynamic field theory. It's like a club or a sect, they belief. So people like really love this kind of stuff, and they work a lot with psychophysics people, like all this cognitive science, developmental cognition, which use these models to explain behaviors, some nitty-gritty details of behaviors, how babies learn different stuff, and then also apply it to robots. So it's all in there. Yeah, this is again like how this reference frame transformation happens. You can also read up in the paper, but if this is a reference, this is a target, what you want is to shift your reference frame and anchor it on the reference object, because then you can apply the stereotypical leftness, rightness concepts, which you might have learned at some point, but you've learned them just like all of a sudden egocentrically, and then you can apply, and then you can decide, is this object to the left or not? And it's going to be graded, right? So here it's very to the left, here it's like to the left, but above will also have a say here. And that's what helps us to model this psychophysics. People don't always say left, they say sometimes above, depending on the shape of the object. The object is, my reference object is like this, I'll have tendency to say that this is above. If it's like this, I will have a tendency to say that it's to the left. And this can also be modeled there. Okay, good. Example number 2. So a couple years later, we decided to, again, have a controller, and now have it a little bit proper controller, as people know it, like PID controller. But we still were on the Rolls chip at that time, so it was only P controller. Also controlling the velocity. Okay, so the setting is the same pushbot, the same Rolls chip. We have IMU on the pushbot, and we can measure angular velocity. We sample this angular velocity very coarsely, like five buckets of different velocities. And we can set the goal, how fast we want this robot to rotate. And then we have built this transformation matrix. You can see that the connectivity here is a little bit maybe weird, right? So these are inhibitory connections here. And one of them, and they are kind of always active. So instead of just summing up, we had one of them is inhibiting and disinhibiting. And this we just have done to have it more robustly implemented on this analog chip. Because summing up to things was very noisy thingy on an analog chip where you have mismatch. So it was hard to tune it to the threshold. But this is like super robust. So if they don't fire, you can have as much input here as you want. And if one of the columns is allowed to fire, because I set the goal here, I disinhibit this thing. No, so these are active, this is now inhibited, so this inhibition falls away, now these ones can fire, and the one that gets input will fire. So that allows us to have it robustly on the Rolls chip. Okay, so this now computes the difference, and we split the difference in two halves, positive and negative, because the behavior is very different for positive and negative. For positive, I have to ramp up, like, so for positive, I have to slow down, for negative, I have to accelerate.
I mean, just a quick comment, it's interesting that you have this kind of disinhibitory control, because that's exactly what you see in the brain.
Thanks so much, we didn't practice that.
The globus pallidus, continually inhibiting like all voluntary movements, and then you disinhibit to gain one of those movements. So,
Right.
so kind of interesting example of why. I mean, people always ask like, why is the brain built that
Doing
way?
that.
Maybe this gives you some insight.
Yeah, like hypothesis, right? But I
Right,
wouldn't thought
dragsters
that-
do that too.
Did-
If you rev the engine,
Yeah.
you pop it, right?
Yeah.
You don't so that's
Yeah.
how a lot of things work like that.
In this example, we're building something on the hardware, like makes you use some mechanisms you also see in the brain. So I think that's one of those cases. Okay, so yeah, so the error can be positive and negative, this D minus and D plus. If the error is positive, then I take the afferent copy of what I was actually doing, right? I had this rotation number 1, and I sum it, right? So I have get 4. If the error were negative, then I would subtract it. And both pathways are always active. I just inhibit one of them. So if the error was positive, it will inhibit the negative pathway. And if the error was negative, it will inhibit the positive pathway. But otherwise, I read out, okay, now I want to have 4. I just map this 4 here. I sum up positive or negative. So which command shall I have now? And this goes to the motor population. The motor population, again, has this characteristic population of neurons. If one of them is active, I rotate a little bit. And if many of them is active, I rotate faster. Okay, so that's my controller. It does the control. It's like immediately jumps to the correct answer, but you know, like wants to be fast and so on. And then there's an additional pathway. We also wanted to learn just the forward control, because remember the chip has plastic synapses. So we wanted to show off and show that you can use the plastic synapses. So we had another population. So these are the commands. So again, the goal, and it has a direct mapping onto these motor neurons with plastic synapses all to all. So if my error is 0, then let's see, then it kind of disinhibits these guys so that now I have this pre and post active, and my synaptic plasticity STDP is active and learns the synapses. So from here to here, this will be active. And because the error is 0, only like one neuron here will be active, the lowest speed, and the connection will grow. The other connections will be pruned away. And then if 3 is active, then because the error is 0, I will actually have 3 neurons active here and rotate with the speed of 3, or maybe 4, right? Because like the mapping between the desired speed and this neural representation is not known a priori, but I will then learn these connections so that I like a priori can have a command and try to directly move with that command. And if the error is 0, I will just use this controller. But if the error is not 0, then I will control with this PP controller and will update my command. So I can have
How do
this.
you get the error?
The error
The
gets,
original.
I get here.
What
right?
sensor measures the error?
So the goal is just set how I want it to have, and then I have IMU. IMU measures my actual speed.
Oh, I see. IMU,
And I-
it's rotation velocity.
Velocity, yeah.
Angular.
Angular
rotation
velocity. This is what I control. This is also what I set. Rotational velocity.
Get the error from the IMU.
I get the error. No, I get the current speed from IMU.
And
Very angular velocity. Very coarsely, like 5 miles. Right? And I have and then I have this thing to calculate the difference. No, this operator, say this architecture for reference frame, the one before, where I read out along the diagonal. And now I just split the error into 2 parts, right? So this is positive, 0, negative. So the diagonal, if I have 3 here and I measure 3, then my activity will be on the diagonal, and this links to the error 0. And if I have 4 here, but I rotate with 1, then I will have error 3. And here the error is negative. Because I have 1 here, but I rotate with 4. Minus 3.
so Yulia, you have another whole bracket like the one on the right for the negative direction.
Yeah.
Right, you're not showing that.
I'm not showing some connections because for negative and positive, I use the same array. I just read out from this array along one diagonal for plus and along another diagonal for minus. So those 2 potentially are always present, but one of them is inhibited depending on which array is detected. And this inhibitory connections on both.
So if your error is 0, you're using STDP to reinforce that.
To just learn the direct connection. Okay, so you know this goal speed corresponds to me rotating with this velocity. And velocity is pretty directly controlled by activity of these neurons. So if my goal is 4, then 40 of these neurons should be active, or like 36.
But it may not be quite a medium after.
Yeah, 36 or maybe 25 exactly. That's why I learned it. And on rolls, it's all like teeny tiny, like 256 neurons. I think we had to use all of them. Yeah, but if I would have 1 million, right, I could do it better.
And can you remind everybody about this parallel?
Parallel, yeah, the boards, yeah. This is,
Product that you went.
and yeah,
What was it
So
doing?
there's rolls chip, and then it's just on the board that allows you to connect it to the computer, do some
Yeah,
I/O.
Parallella
No,
was-
sorry. Parallella is like an Arduino Deluxe, right? So Parallella was one of these small computers, which we used as a host computer for rolls chip.
I thought it was special because it had specialized hardware on it.
It has a little auxiliary tracing also, but we didn't use it. Yeah, so it had some, little accelerator for neural networks, but we didn't use it.
Did you actually use like a one-hot encoding as from here, or is it?
I will come to that in a minute. Like this representation, we'll say a few words, but yes, of course. And it had to be 1 hot because we will literally have 5 neurons to represent rotation speed from 0 to 100. 5 neurons, you have to use 1 hot encoding. Otherwise, I would use some soft maths.
So my intuition for this field is really like you're doing like you're looking at every possible combination that would have an error of +1. They are, for example, 1 diagonal, and then by summing them, you're just saying like if either of these is all right, it's like a destructive normal form or something.
Yeah, because it's one hot, it will always be 1. That's a good thing. Otherwise, it would have some illusory conjunctions. Okay, let me accelerate a little bit. Okay, so we did it for P controller, we did it for PID controller for controlling the little drone. This was in one dimension, just controlling the angle. And the PID, so for those, I think everyone knows, right? You have the error, and usually you not just send the signal proportional to this error, it's also useful to send two other signals, one proportional to the derivative of the error, how quickly the error was changing recently, and integral. So what was the sum of the error recently? Like, John's world, it's proven that that's what you should do. So your motor signal is sum of this proportional, integral, and derivative terms with some coefficients, which are the black magic that makes it stable and work well. Okay, and then another caveat that's on the drone, we don't control the position directly, we control the speed. So we needed kind of two nested controllers. First we control the speed, and then we control the position. But that's okay, this was the time when we had Loihi and not rolls anymore, so we had enough neurons to just do whatever we want. Okay, and here's representing values. And this is one of the questions that I only have neurons, I don't have integers or floats, I don't have numbers. I only have those neurons. How do I represent numbers? IMU gives me a number between 0 and 64 in this particular case. What I can do, I define a population of neurons, maybe a vector, and I set like each one of them responsible for a range of these values. If I have 5 neurons, then the ranges will be large. If I have 64 neurons, then like 1 for each like value between 0 and 1. And it's very efficient representation because one spike here already encodes the whole value, the whole integer. If I know that the spike came from this line, I know that my measurement was somewhere between like 2 and 4. Like a very efficient representation. One hot, one spike is enough. And this allows us to be very fast. Remember, we need to control this drone, we'll be very fast. Yeah, identity of an active neuron represents the value. Each spike carries this value. Population code could account for uncertainty. So if I have enough neurons, then I could have like a population of neurons that represents some value, and then it could be like broader or narrower my representation. Okay, so that's our PID controller. Same motives always, right? Set angle, this is the angle that I want to have. This is the angle that I somehow measure. This is the difference, the error. The proportional term, I just give this error further. The integral term, I keep the previous kind of error here, and then I sum the new one with the previous one. I keep the previous one actually here, and I sum it with the current one, so I can integrate. And here I keep the previous one around, and I subtract from the previous one. It's like a proxy for derivative and integral. Make it precise, maybe you have to play
And so
around
then
with
the
those
subtraction will be along there.
on the diagonal. So the main diagonal is subtraction, the other diagonal is summation. And then you move the bump either left or right. That's what the subtraction is the right and the other one is left, and I go to distinguish that right. So yeah. Okay, so velocity command, and it works, right? So we can move this very annoying and noisy drone, right? So these are different set values that we have to the target, and then it kind of converges. I don't know if it's nice convergence or ugly, but it's the control. Sorry?
The gains.
The gains we tuned in this case. I'll come to gains learning a little bit later. Yeah, so we can set the different values and then things like that. In the later paper, we connected it to vision. So we had a drone that has a DVS. We put a little like horizon in front of it. It was rotating pretty quickly. And now the drone had to track this horizon. So we added a very like simple network that does visual processing. It did basically half transform. So it would transform lines into dots, right, in this half space, and dots into lines, right? So every event will create a line in this half space, and where they cross, if they lie on one line, they will cross, and the point of this crossing will give you the parameters of the line. Half transform, you can put it for it. So the half transform dot is a line, and where they intersect, so that it shows you the line in the original space. Yeah, so kind of with one layer of synapses, we have a parameter of the line, and if this parameter is like the angle is not the one that we wanted, that's our error. Then we can easily compute it and control. Yeah, so we had a very fast visual controller, right? So it's a real recording. Like these are these lines where they cross. We have the estimate of the thing, and then we had 200 microsecond latency and 20 kilohertz of visual control rate. That was running on Loihi 1. It's mounted somewhere over there. Good old times where you could directly connect DVS camera to this chip with parallel interface. Every event would directly go to neurons. Spikes of neurons would directly go to the computer, to the host computer.
So the US camera is on the drone.
It's on the drone with up board with a little computer that does like events, and then it sends the rest of the visualization, data recording that's sent to the laptop. Yeah, 2020 COVID times was a lot of fun. Yeah, so, and now this weight haven't done, so we haven't shown, but in principle, these weights could be plastic. I think actually, no, we had one work. So I think in master thesis of Vitale, he had used some heuristics that people would usually use to tune automatically the gains. So there are some heuristics like when you change the derivative gain and the integral gain, like what you have to observe in behavior of the error to change them. And we kind of implemented these heuristics and made these weights plastic, just pushing them a bit up and down. And there was this paper, it was breaking news, so it never made it out of breaking news into solid results. Yeah, but in principle, you can do that. Yeah, you can learn the gates, adapt the gains, learn the inverse model, learn non-linear, non-constant across control range gains. Yeah, that's really stuff. Okay, third example, saccades enriching. So saccadic eye system is a very, overall eye system is a very special thing. I'll use it as an example to show how you can do control using some kind of motion primitives, some kind of maps for amplitudes of your motion primitives, parameters of your motion primitives, and how continual learning plays a role there. Okay, so eye movements are amazing. I first met them in the middle of the 80s, and I was like 3 at that time. I was reading this great Soviet encyclopedia, and there was this picture there, and I found it fascinating. That's how I got interested in neuroscience and all that stuff. Right, so the eye movements are an interesting thing, right? You do all this stuff, you do saccades, you do fixational eye movements, smooth pursuit, microsaccades, there's all this vergence, and you use all these signals, both the motor component and all this movement, to generate this illusion of a stationary perception, and also to anchor, I would claim, the body reference frames on the environment. So I think this looking around is very important to be able to do all kind of stuff relative to objects in the environment. That's our only access to objects in the environment until we touch them. So I think it's very important how we look. That's why in one period of my life, I found it interesting to build saccadic eye movements. So let's have a look. Saccadic eye movements is, there's an eye, there's a target, and I can do this. And that's not trivial. Like, the target is somewhere in my retina, and I know how to control the muscles of these guys to land exactly on this thing, very precisely, wherever this thing is. Quite amazing. Okay, so saccades are precise and fast, so ballistic, feet forward, eye movements. The second fact about saccades is that they are adaptive, and you can show it in an experiment. So what people do with other people is that, there's a target, and you try to move there, and while you move, it does like, the target moves. And you don't notice, because during the saccade, you're blind, it's fast, and there's some saccadic suppression, and the experimentalists say, let's shift the target. So when you land here, you're like, oh, oops, missed it, and you do correcting saccade. And you do it subconsciously, so you don't even notice, but your eye jumps on the target. So you do it 200 times. And what happens then is the following. The experimentalist moves, and you, and you do the saccade of the right amplitude. It's not right anymore for the rest of the world, but this experiment is the right one. And you can, within minutes, change that. So it means the saccadic, sorry?
And you get a headache, like when you get like
these experiments when they turn around the whole world, it's like, yeah. And it makes sense, you drink a bit too many cups of coffee in the morning, your motor system is probably controls slightly different. You drink something else in the evening, right? Again, the control changes. So the system is constantly adapting, right? So this controller is constantly trying to stay in sync with the world, because looking at the things and knowing that if I see something here, when I move my eye in a certain way, it will be in the center of my visual field. Knowing that is very important, and I'll argue in a couple of seconds why this is important. Okay, so we first built a model for that. So continual pervasive adaptation.
You said it's open loop. In what way is it open loop?
So that there's no visual surveying. It's not that I see this target and I drag myself to land on the target. No, I do one movement. I know the vector, the motor vector that I need to send to my motor. I see the dots. I don't do visual survey, no time for that. And no feedback, because the feedback is suppressed during the saccade. So I have to learn it. Okay, so that's the minimal model for the saccadic eye movement. So now here's my perceptual field. I have three objects. Visual field, signal field, I see some things, my working memory, and the visual field. See, this is the selective field. I select one, oh, that's the target of my saccade. I want to look there. Superior colliculus, maybe something like these lines there. And then on the other side, I have my motor system, and I would claim that there are kind of motor primitives controlling my eye to create this ballistic eye movement. And these motor primitives, so I model them as a little oscillator, a Murray oscillator. There's an excitatory neuron that drives the motor system, inhibitory neuron that excited by excitator inhibits it. This generates an activation of this neuron like a little wave. The neuron ramps up, then inhibition kicks in and puts it back down. So it's a little oscillation. And then I have another neuron that controls, I have done one oscillation because it's useful to know that I finished my saccade. It's useful to know for the rest of the system. So I have these three neurons that have an oscillation. I can switch the oscillation on. I know when it's done. All right. And I use this signal to drive my eyes in terms of their velocity. So velocity is 0, then it's maximum, then it's 0 again. And I do saccade with some amplitude. Which one, I don't know. I have to calculate the integral under this curve, but some amplitude. I don't care because I can learn it. And I have one for vertical and horizontal movement. And interesting, this vertical and horizontal doesn't have to coincide with vertical and horizontal on my retina, right? Because on the robot where we've implemented this, our motors were shifted, right? It was some configuration. So my vertical movement, horizontal movement was some arc on my retina. And for the eye also, like, who knows, like, what the mapping is, the muscles, what they exactly are doing. Okay, so what I can control, what I want to control, so this creates some stereotypical up and down to 1 and back to 0. And I want to control the amplitude. By controlling the amplitude, I can control the amplitude of velocity. I can control the distance to which I go, the integral under the curve. Why this way? Because for saccades, there's an interesting fun fact that for many amplitudes, the duration of the saccade is the same. I do short saccade, it takes, I don't know, 100 milliseconds, 300 milliseconds. And I do long saccade, it also takes 300 milliseconds in some range. And it's probably useful for the system, for the rest of the system, to know, like, I will be blind for 300 milliseconds and not longer, and then I will land on some target and can expect something there. So it seems to be important that this timing is controlled. Okay, and here I control the timing. I'm done with my saccade after this time. Here the velocity is 0, and I control the amplitude by how high I go. So then I just need some multiplicative signal here, and I need a map of these multiplicative signals, depending on where my target was. My target was 60 degrees. I need a high value here. I will do big saccade. And if my target is here, I need a low value. I do small saccade. So I need to learn a map that looks like this for horizontal saccades and for vertical saccades. So I take this activation, and then I use it to know from which part of my map to take the value. I just calculate this value and then multiply this value with this activation. And I get my velocity signal. Very simple.
A small question. I've heard of people talk about microsaccades.
Those are different systems.
Those are different systems. Yeah.
I have them a little bit here.
Okay.
In a larger architecture, because of course that's the minimal thing, right? But to do the minimal interesting thing, this learning, I need a few more things, just a couple. So here there are my oscillator. It triggers the saccade and knows when saccade is done, and then I have this fixation node. Here I could do my microsaccades to study the object, recognize it, enhance some features, whatever the microsaccades are doing. So here I do this, and this is a different behavior, elementary behavior, which I will come to. I'm not finishing on time, but the others are also not finishing on time. Okay, then I have another module. So I have this target estimation of error direction. So this I introduced because to learn, I need to know that I made a mistake. I did a saccade and I didn't land on the target. And I have a very simple error estimation module. It just tells me, was I too far or was I too short? Because if I was too far, I will just bump my map locally a little bit down. Don't be so rigorous here. And if I was too short, I will bump it a little bit up. So my learning rule here can be very simple, right? It's just, no, signal comes, go down, signal comes, goes up. That's it. And the location where I do it is defined by, where my target was. So my target sets some neurons here. It's presynaptic input. So only those neurons that have this presynaptic neuron will have this plasticity. And then when this guy is active, it will trigger either positive or negative plasticity. Super simple learning rule. There's another gain selection, motor memory, where to adapt. Because you see, so now I not only have one map, I have a whole series of maps. Because it happens for different reasons, I think, in the eye and on the robot, that depending on from where I did my experiment, where my motor system was when the target was shown, the motor signal that I need to show to look at to express, to look at this target is different. On the robot, because I have this complex configuration, on the eye, you can imagine if I look left and I have a target 2 degrees to the left, the motor signal is different if when I look right and the target is 2 degrees to the left. Here, now I just have to go, and here, so this maps.
So are you just saying retinal versus body coordinates?
No, it's that the maps depends on the position of my eye before the saccade.
Because it's not linear.
Yeah, so it's not only depends on where the target is on the retina, it's obvious, but also on where my eye was looking before the saccade. Yeah, because the motor plant is not linear. Yeah, like here, because the muscles, right, they have more tension here than here. Right, so if we're going to the left, and on the robot, just because I have this, so I have like a little geometrical system there that drives it. Yeah, so I have a whole system of maps. You know, was okay in terms of computing how it's all can run in real time.
Those marks are getting the kind of like model state.
Yeah. Yeah, so they get the motor state of the eye before the saccade. Yeah, to kind of select them up. So it's again 4-dimensional thingy. Yeah, so this is how these maps look, actual maps that we learned on the robot. And they have some like shapes that reflects maybe the optics of my camera. Right, so I think that's what you see this aberration, yeah. But they also differ for different positions of the initial positions of the camera. And here's the adaptation experiment, like, you know, because the maps they constantly learn. If my saccade was wrong, I update the map. This is how I arrive at the map in the first place, and I constantly update it. So here you can see there's this little region that became from yellow slightly greener. This is because I was playing this experiment. Like for the targets that are here, I was shifting them. So this position got kind of slightly inhibited locally. And it's also what happens in experiments. So this shorter saccade, it's not that you do all saccades shorter, only to that position. So it's local. And we show how this no adaptation. Yeah, I think we could run like most things and align it with some experimental stuff. Didn't. Okay, eye movements 3. Oh yeah. The third fact about eye movements. The third
So how
one.
many neurons are you using for that?
So how many neurons? Like, no, this thing would usually be 100 times 100, 10,000 to have this nice peak like that. So 10,000, 10,000, 10,000, 10,000. Here you have maybe 20. I don't know, depending how you want to sample. But you know, it's less than a million.
But on a related note here, right? When you were saying earlier, like it's very efficient to have like one neuron is firing and that tells you where in the vector you are, right? But I mean, it's on the Lee or similar systems, you're kind of then you are encoding the position of the neuron by an address, right? So you're again sending like an 8-bit value or whatever to encode an 8-bit number. So it's like it's efficient in the sense like from a biological perspective, if you actually hardwired everything, it would be efficient. Yes. If you do it in a neuromorphic hardware, you're back to using this, you know, like binary encoding. Right?
That's true. So here we hope that someone will develop a hardware which is more like biology, right? And where these connections, right, this is efficient. If that doesn't work out, then yes, maybe we need to look for some more efficient compression or whatever for these representations. Maybe. Okay, third fun fact about saccadic eye movements, you can do double saccades. Won't believe it, but you can, and it's not trivial. That's maybe what you didn't realize. So the experiment goes like this. There's an eye, and there are 2 targets shown, and then they both disappear. Could you please look at where these targets were, right? And we can do it, because grown-ups can do it. Kids don't do it very well. Kids could do a different thing, but you can do it, right? You believe that you can do it, but that's not trivial. Why is it not trivial? Because look, you saw these 2 targets, and like, you know, they were on your retina very briefly, poof, poof. Right? And so if you just remember these targets and you immediately store the motor vector, how do I look at this target? How do I look at that target? Right? That's what the kind of you assume. And what will happen after the first saccade? Remember, this is the motor vector that you remember you need to do. And it's all very quickly, right? So no time to think. You would look there. Right? From here, you would follow this vector and look there. And this is what kids actually do. They do these mistakes in double saccades, and they actually follow this vector. But with age, you learn to use a different vector, meaning that when you were here, you stored this target. So two options. Either you stored this target in already correct vector, so you did this transformation before storing, that you knew that where you will land, or you do the transformation like after this movement, you apply the transformation. And I think it's still like debating which one it is. But we had to make our choice because we wanted to build a system that can do this. The target positions are transformed to gaze direction independent representation. I'll tell you my hypothesis there, and I'll show you the horrible architecture that's possible to parse. So my hypothesis is that at this moment, we store these targets, not in retinal coordinates, not in some allocentric coordinates, but in coordinates of what motor state shall my eye have when it's here, and what motor state shall my eye have when it's here, in the motor state. Like, no, like, how will it feel when I'm there? Because these motor coordinates, they kind of mine, right? So if I represent stuff in these motor coordinates, I can then link them to everything else, like to arm coordinates and, like, you know, to other coordinates that I can control. They're internal to me, they're not anchored on anything abstract out there in the world. So if I move around, they're kind of still valid. Okay. 7 minutes over. I'll take another 2. Okay, so that's what you need to do to do that, to do double saccades. I won't even try to just to highlight, like, you know, you have this visual perception, you have different objects, you store kind of multiple objects, so you need some memory for multiple objects, and you need some memory for multiple motor command kind of integration, and you can do gaze planning based on the visual input that is in front of your eyes, or based on this internal representation in motor coordinates. Yeah, you have the gain maps. There's a paper that describes it horribly. Yeah, and there's code somewhere. Maybe it's also working. Who knows? Yeah, so I wouldn't go in detail there. But that's control. And then the last bit we did in this vein is learning to reach after learning to look. So if you have this gaze direction space where you store your objects, you can learn once and for all a mapping between this gaze space. Like, you know, when I look there, then I know it's all like my body coordinates. Then for my arm, I need to use like these coordinates to get there. So this is XY for the arm to be there. And I kept it to XY above the table, just not to have 3-dimensional things to coordinate. So they have this angle of the eye, and we have proprioceptive space for end effector of the arm. We can learn the mapping between the two just by like looking around and putting my end effector in the center of my visual field. I can learn this mapping like once when I'm a baby and, you know, playing with this twice. And I update it, of course, as I grow, but it's kind of my thing, which I can now use to anchor visually perceived objects in my motor space so that I can reach for them. And then you need some, you know, behavioral organization, you need some state machines to learn it autonomously. Okay, done. Model predictive control, I will just flash, that will really be a flashlight. To know what is model predictive control? It's when I pre-calculate the trajectories that my body will have, and I pre-calculate all possible trajectories based on the model of my motor plan that I have, and then I select the best one, doing some optimization. And what people have noticed, people who joined Intel at some point, that these spiky neuronal networks on chip are pretty good in solving optimization problems, certain optimization problems. Like, for instance, train scheduling problem. They've shown you can do it like 10 on 5 orders of magnitude or more energy efficient energy delay product. It's better for solving these large scale optimization problems. When, you know, I have some states, I have some constraints, some states not be active together, I'll scan, and then I want to find the solution to this problem. So some problem that will minimize something like travel time in the system. So what Intel has done in the last year or so, and now the paper is actually out, officially it was in archive for a while, is that so we worked with Marco Hutte together. They have this MPC, model predictive control for animal robot. It has a very good model of the mechanics and dynamics of this robot. You know, it has 12 motors, 48 sensors, I think, like IMU, and then different directions for every motor. And you can kind of compute the trajectory based on maybe some coarse visual input as well. And then you have this optimization that selects the best trajectory. And it's a pretty big optimization problem. They managed to run it in real time. It's only a second delay. We wanted to do the same, and we managed, or they managed. So I put them together, and then in the work I was not involved. In the paper, they describe how they do it. So in this model predictive control, you have these matrices that describe, you know, the dynamics of your system and the cost like of your system. You don't want to fall, like, you know, different constraints on the joints and so on. And then these matrices can then be expressed as neurons and connections between them. And then you just let the kind of activation in this network bounce around, like relax, to a state that corresponds to the most energetically, whatever best state that optimizes your cost.
But you have to modulate your strength of your connections.
Yeah, you have to, yeah, over time, exactly. That's a bit of a bottleneck, but on Loihi you can do it with this microcode. And every time step you can do some change there. sort of using all the bells and whistles of Loihi. Loihi, you can define the model of your neuron. You can do that. You can change the connections. Yeah, and it's a pretty large system. So what has been achieved, and that's the result. Then I think so. It was 2.5 times faster than Makuhuta's system. I would take this number with a big grain of salt or whatever. Because it's this kind of simulated thingy, right? So I think on a real device with I/O, maybe yeah. And energy was 200 or 500 times. So yeah, 200. So I think energy was 200 times lower. So it would be if it would run on Loihi and everything would work perfectly with compiler and so on. It would be more energy efficient. But I think it would probably be faster actually. Yeah, that's the result. Okay, and the last bit, elementary behaviors, just to mention, like I mentioned this hierarchy in the last end of my list of what control is about. So you have continuous control, and that's what we were looking on so far, how you control continuous variable to deal with certain value. But then at some point you have these discrete actions, reach for something, grab something, look somewhere. And a lot of like what the brain is doing is switching between these discrete things. So we at some point like postulated that in order to control these discrete things, we need some structure. It can all just be like, just neural field and that's it. So we call this structure elementary behavior, and it has a pair of neurons in its simplest form. One is intention, one is conditional satisfaction. We got inspired by terminology used by John Searle. It's like a philosopher who thought about intentionality of action. So the intention node activates the behavior. Now it primes your sensory system to be sensitive to something. Maybe in the spatial language architecture, it boosts the target field and the color dimension. Maybe it activates some controllers. So it sends some positive activation to your sensory motor system, do that stuff. And then the conditional satisfaction system monitors when that stuff is done, when you're done with the action. Then it's active. Okay, I've finished that. So for instance, in this connection says, so what do I expect when I'm done with this action? Like when I grasp, or typically I expect certain sensation on my fingertips that grasp. That will make this thing activate and inhibit my intention. Now I can do something else. What else depends? Maybe I have learned the sequence of actions. Maybe my environment tells me that's the next good thing to do. Like I do something else. Now we have a slightly more complex thing with this condition of like failure. We needed that. We use this architecture not just to generate action, but also to parse actions when I observe them, to know now this reaching is now done, now the grasping is done, so that I can observe someone doing actions and parse sequences. And then here we looked at a bit more extended version of that not only has conditional satisfaction and intention, but also motivation and precondition. The precondition inhibits certain intentions because they need something else to happen. Like before I close my hand to grasp something, I need to be there. So like my grasping is inhibited until I get there. So it kind of tells me to establish a sequence of actions. And motivation kind of tells me, hey, you might want to activate that action. So you want to grasp it, you might want to activate reaching to get there. So it kind of sends the activation in another direction. So with these four fields, we can do something called simultaneous planning and acting. Planning and action, where you can set the goal, and then you'll have like activation spreading in a system. So I want to get there, so I need these guys activated. They are not activated because I'm not at this position in space. It's like an agent moving in a maze. And then this activation spreads until it reaches my current position, and then I know the path how to get to the goal. And I just go there. Yeah, so the MATLAB code for that is working. That's how we can play around with that. Yeah, we've used this concept of elementary behavior a lot. So Matthias Richter, some of you might know him because he is one of the contact people at Intel now in Germany. So it was his master thesis. When we had this little robot, we wanted it to look at objects and then grasp them either with left arm or with right arm, depending on where they are. And this is the architecture that does it. So it has these elementary behaviors for find object color, move head, look at this object. Because again, when I look at the object, I can use the motor state of my head to know where to go with the arm. That mapping can find and affect the marker color, so to know that I have reached the object, I have a little marker on the finger, so I know that I'm there. When I'm done, I can do open gripper visual surveying, so I have this coarse movement and I have fine movement to really align my hand with the object, move arm, close gripper. Yeah. It's the behaviors, and we've shown how autonomously the robot can just act with this red object.
just one question, because in the picture on the left, like there's a lot of objects on the table, on the right there is like one object. So for the one where you have a lot of objects here, how do you do this? Like if there's many objects, like, do you have much higher dimensional maps, or do you have many maps, like one for each?
So I have one map somewhere where all objects are there. It's like saliency map, potential proto objects. We didn't use this proto object, but in some other work we did. Here just everything that has some that's not white basically is potentially object. I could use height, some feature, and then I have this color channel as a hue. When I color, then I set a color filter kind of, and then only red objects pop up. I still might have 5 red objects. They go in a selective neural field. Winner take all architecture just selects the one that's maybe bigger, maybe closer to the center. Like maybe I have another queue that tells me which object is the best to select. Randomly selects one, but sticks to this selection. It creates this sustained peak. It doesn't care about the others anymore. Yeah, and this was actually done in Telluride, I don't know, maybe 2014-ish. Yeah, so these guys, they just move. Now, this has like Python implementation behind. I don't know if we accelerated it or not. Here we additionally took into account if the object is like horizontal or vertical. You know, I have a graphic like this. We had some affordances of graphic like this. Yeah, that's me. That's in the elementary school.
What happens if you change the weight of the object? Does the controller still work?
So here you have to realize what this robot is. That's an hour robot. It has these fingers that have like close and open, super wobbly and no feedback whatsoever. Like it can grasp this object. It's magical. It's like state of the art. Because usually what this robot is doing, like it maybe shows you some Tai Chi or yoga. So nothing grasping. If you have an arm that has feedback, right, and you have force control, like here, like no force control, it's all position control, then you can do everything.
Now it overheat, we had to take the head off and blow a fan on it because it would just overheat. You know, doing nothing at all, right? It would just overheat.
This is 2011, 14, right? The robot is still there, but it's somewhere between the toy and the research. This robot. And yeah, hierarchical. We had an EU project running for 4 years, so we've done a lot. Okay, almost done. Look now. You know, how many of you actually know VSA? Yeah, I'll skip. So we had these 2 recent papers in Nature Machine Intelligence where we have done some of this stuff like visual odometry, control of the robot, scene analysis with vector symbolic architectures. I don't know if maybe Michael, you had maybe a lecture on vector symbolic architectures. Okay, so there was a lecture you might know. So this kind of a very different representation for like neuronal population, equivalent for neural population, with which you can do somewhat similar stuff as you can do with our neural fields. So what I wanted to briefly maybe look at these 2 worlds, neural fields, and those are these peak-like dynamic representations, and symbolic vectors. And the first thing that you might notice, there are these software frameworks that look like suspiciously similar. You know, you can drag and drop neural populations, you can connect them, and then you can run the system. I think ours was inspiring, but yes.
Oh, sweet. I thought it was the other way around.
The co-developed.
Keep very happy.
So maybe very quickly, just to finalize. You know, both these frameworks, they use population code. So they use populations of neurons. Here are these fields, they're populations of neurons to represent stuff, represent numbers and variables. And here as well, populations of neurons, like vectors, can be seen as populations of neurons to represent stuff. The difference is that here these populations are structured. So they're defined over some metric spaces. Like here I have position on the retina, or maybe color, or maybe some 2-dimensional space. And they, like items close to each other, they represent similar things, similar colors, positions. And here they're random, which has an advantage. Like you can represent more this way with combinatorial representation. Like here we have this winner take all kind of structure. Here you have some high dimensional maths. Here you have bumps. This is easy to design. You just make random vectors. I only have 3 items here.
So just a quick comment, like in the brain, the VSA, that looks like sensory codes, and the neural fields, that looks like motor code codes.
Interesting. Okay, I'll maybe argue a little bit on that, like a little addition. Last line here, you will appear in a second. Okay, the second similarity is that they kind of use and define these neural operators, so operations, like binding, and then this reference frame transformations that we've seen. This is the same thing. You have then bundling, when you just sum 2 vectors 1 to 1. We also have something similar with pre-shape. So these peaks can with pre-shapes, and the pre-shape just sums them. So we have some very similar elementary, next after elementary operations. We bind ourselves like in DNFs using only connections. I think you're a little bit freer and can just use math.
Yeah, well, but neural networks can approximate any math you want, so I can do that.
True. And the common thing that there's some dynamics happening there. I would claim that we emphasize more dynamics within populations, winner take all, that makes a peak emerge, the bounce selection. And you cannot do this within the vectors. You can to some extent.
We haven't done it as much as you have.
Yeah. But you have these dynamics between the populations and this resonator, for instance, architectures, and those are very similar. Yes, my conclusion is that maybe these guys are actually on the sensory surface, so not only motor, but also low-level sensory, like where you have maps, where you have color map, or just retinal position.
I mean,
And in your theory, it's connected anyway. Motor and
we
sensory.
could have to discuss more, but I mean, I think like the issue with sensory codes is that it's just very high entropy.
At
and
some
so-
point, right, in the higher level. So that's why it
No,
takes.
just throughout the system, it's high entropy, and
and don't forget-
that's why you have these kind of.
And don't forget that these things are not just on the surface of the cortex. They have to project them into these behavioral spaces, like in the color space. The neurons that are on the line here, they can be spread like pepper and salt on the cortex.
Yes.
You don't see them.
So this thing is like the layer of 5B pyramidal tract neurons.
Projected onto behavioral space.
Yeah.
So whenever you can project in behavioral space with some metrics, then I think like these dynamics are again useful. At some point you cannot anymore. If you go in the space of concepts in a chair, democracy, population dynamics, then maybe this is some more representation.
I was gonna say there might be an even more fundamental relationship between these, because if the dynamic neural fields are like a superposition of positive definite kernels, then there is a vector representation for that, and vice versa.
Yeah.
So it might really just be a matter of which representation is more efficient.
Yeah, so it's probably the same thing, it just projected kind of into
Yeah.
different spaces. And then the question is indeed what's efficient, maybe running on hardware, maybe like, whether I know the metrics or not, and then it's good.
Yeah, I mean, there's another fundamental difference here, right? Because those structure representations, the way you've shown it, that's like an Euclidean space. Whereas what if you want to represent something in a hyperbolic space or something? So kind of like the
Yeah.
geometry of
So I
the
agree.
space, that's appropriate for it.
Yeah. Yeah.
Like these concepts that are hierarchically related,
Yeah.
much better to hyperbolic space.
Right.
So there's another dimension.
Yeah, good. And like, in this paper, so I thought we really wanted to use these VSAs throughout. So he has forced space, like very like intuitive thing, into vectors. So every position would get a vector, 10,000 dimensional vector to be represented. And that was maybe a little bit stretching.
Yeah.
Okay, my last slide is very briefly to come back to everyone who was sad this whole time that they banned deep learning. I kind of unban it a little bit. Like first, like, what is control? Control is a feedback-based error correction. And in deep learning, this is also what happens during training. You do feedback-based error correction. But this, because you do it like only once and for life, it becomes very costly. In control, you want to do it all the time. And that's why you are forced to do it cheaply because you need to do it quickly. And it forces you to maybe develop slightly different architectures, maybe not so bulky, maybe smaller like things and many of them. The second one, control is about closed loop systems and recurrent. And deep learning is not like that. Deep learning is straightforward only, no recurrence, no state. Now there are the stateful models being like appearing this year. But because it doesn't have this recurrence, then it's forgetful. So it needs to store everything in those weights, and this makes them again costly. And remember, the cost is maybe the main problem with deep learning today. So if you make deep learning more like control, we might solve this problem. And our control kind of focuses on behavior, what we want the system to do, what we want our robot to do. We want it to grasp things, go to places. So we focus on the kind of behavioral targets, useful targets. While DL is about information processing. We want to, optimize how many classes we can represent, and we want to classify with a certain accuracy, 99%, 98%. So we kind of chase these information processing objectives. And it's also needed. We want our systems to be like maybe optimal if you want to like recognize different classes and so on. But the research and terabytes of papers and person months cannot be only about that. For your patience.
Yeah, we're a half hour into the next talk, so let's give a 5-minute, very, very, very quick break and.
Okay. So for this morning, I'm gonna talk about how we look at star data and satellite data, and really how we go from the raw data captured by the sensor all the way to satellite information factorization, which is really where the application lies. And we're going to touch on somewhat complicated topics. So to keep it somewhat grounded, I'm going to make it very practical oriented and start with data that we collected a few days ago in Telluride with the little thing right here. So really just pointing a lens at the sky and seeing what the sensor captures. So if you do that using the camera, you get essentially this thing, a lovely star field. And if you pay close attention, you'll see an object moving in a slightly different direction right here. It's easier to see if you speed up the data, and you can see very clearly that there's something moving in a different direction. So the very practical question really is, can we figure out what satellite that was, and how do we do that? And all the techniques that I'll present today to do that are very conventional. None of them would really qualify as neuromorphic. But the point of the talk is that we'd like to make them far more neuromorphic, especially as we look to move those systems to space where resilience, power, efficiency, speed really matter. So keep in mind that really the point is for us to collectively think about how we convert those very conventional algorithms to something more spiky or more neuromorphic, if that makes sense. Okay, so the very first step to getting anything useful out of the data is to segment object. We want to know where the stars are and we want to know where the satellite is. Before we can do that, we typically need to do a bit of cleanup. So on the left here, I have a normalized event count. So basically take the entire event recording, count the number of events that were generated by each pixel, and build a map of numbers and represent that with a color map. If we zoom in a little on one of the regions here, we see that actually there are only a few pixels that generated a lot of events. Those are the hot pixels. And otherwise, we have a fairly uniform amount of events being generated. So before we do anything useful with the data, it's usually a good idea to filter out those edge cases. So typically remove the hot pixels. We would also want to remove the background noise. Here I'm using a very simple algorithm to do that. If a pixel spikes in isolation, we remove it. It's probably background noise. And if there's structure around a particular event, we keep it. I'm also removing the off events. That's not always a good thing to do, but in this particular case, we've come to learn that with star data, off events aren't all that useful, and you get most of what you need with on events. So after doing that, we go from 200,000 or something events per second, which is reasonable already, to only 11,000 events per second. And that's kind of the point of looking at space data. It is very sparse and thus fairly easy to work with, even with current cameras, we don't generate all that much data. So here, this is the zoomed in version. I'm probably being a little, I have probably too strong a background noise remover, so we're creating a few holes there. That's probably fine. We still have plenty of events to do what we want to do. Okay, so now that we have this cleaned up data, what we'll want to do is figure out the speed of the different objects. We want to do motion computation so that we can more easily identify the sources. And perhaps the most visual way to do that, so this is my event data after filtering, and we can look at it in 3D, right? So the third axis would be time. And the technique that we use most often is called contrast maximization. And the idea is really to say, oh, I should mention, so this is the XY space. I'm projecting all the events in the XY plane. I can do the same thing in the TX plane or the TY plane. So just different ways to look at this point cloud, right? So in the TX plane, if I wanted to compensate for motion, what I would really want to do is make sure that those lines are horizontal. So the position of a given object is now not changing over time. And that's really what we call a shear operation. So if I move my volume like this, which is going to be a very simple matrix operation, so GPUs are really good at doing that. Well, that said, we quite often implement that on the CPU. So here, I've compensated motion just by shifting my events. And I can do the same thing in TY. I can play with the Y speed to change the value. Where it really pops, I think, is if you look at it in XY and do the same thing. where that motion compensation is really just gently aligning all our points. There we go. So in one sort of transformation, I not only compensate for motion, but I also make it far easier to segment those different sources with a very simple clustering algorithm, for instance. Look at that in a minute. Interestingly, another thing that I can do is also try to compensate for the motion of the satellite. I can use different values to try and get that line. Something like this. That. And is I can't reach my controls. Sorry, just a sec here. Here. Okay, so I'm just changing the opacity of my different events to better see the difference between the stars that at that speed as sort of their events are spread out in that projection and the satellites, which if I find the right speed, should become neatly concentrated in one point. There we go. So what we can see, however, is that the stars are generating so much data that their events are still very strongly visible in this projection, even if we're matching the speed of the satellite. And as we'll see in a minute, that can be a bit of a problem. So far, so good. Okay, so the idea behind contrast maximization is to perform those transformations and try different speeds and see which one gives me the most alignment in a manner of speaking. And the way to measure that is with the contrast of the resulting image. If my stars are spread out, I get very little contrast. Pixels are sort of uniformly bright. However, if I'm trying to get alignment, I get very dark pixels and very bright pixels, and that's what I want. One way to measure that is with the variance. There are other functions that can do that, but variance is pretty simple and it works quite well. So if I build the velocity space for that, and that's a very expensive picture, we're looking at 256 by 256 pixels. That's about 65,000 projections. Each projection involves 100,000 points. So this is by no means cheap. But I do see a very interesting hotspot here, which matches the speed of aligning my stars. There is also probably the satellite somewhere here, but it's really, really faint, and thus not visible in this figure. Practically speaking, we usually don't bother building the entire velocity space. I just think it's neat for visualization. We just simply optimize in this space. So start at 0, 0, and then descend the gradient to find that hotspot. So you don't end up calculating 65,000 projections, perhaps a dozen to find the point. And that's a pretty neat space to optimize things, right? It's nice and convex. So pretty much any optimization technique works quite well to find it. So if I use the same technique as before, where I just count the number of pixels and represent it as a map, at that velocity, I get something like this, which is way easier to work with because now we have neatly isolated objects for the stars. And I can apply a fairly simple computer vision technique where I'm going to look at that projected flat to the matrix as an image, and I'm going to binarize it. So pick some threshold. If the pixel, the number of events, the even count for that pixel is above the threshold, pixel becomes white, otherwise black. And then you can use perhaps the simplest clustering algorithm to solve that problem, which is just connected components. If two pixels are side by side and white, they become part of the same cluster. Otherwise, they are different clusters. So what I've represented here are those clusters where different colors indicate different labels. So this is very conventional computer vision with images so far. Now what I can do is, now that I have those pixel labels, I can look at the events that were generated by those warped pixels and use that to label the events. And I have a nice clustering of my original events. The point of doing that is that those clusters are not uniform. Some of the pixels in each cluster generated far more events than others. So if I zoom in and look at what it looks like with events, we see hotspots, which are probably the center of the point spread function generated by each star when looking at it through a telescope. And I can then apply, just search for the center of mass of the events, and that gives me a center for that particular star, and that'll be useful in a minute. Okay, so now that I have my stars, and the events associated with them, I can remove those events from the original event recording and do the contrast maximization again with whatever's left. And now, interestingly, we get a second hotspot in the velocity space, because now the satellite signal has become quite strong. Because my original clustering wasn't all that good, I'm using fairly simple techniques here for the sake of illustration. There are still quite a lot of remaining stars. So we still have a second spot here. So I had to cheat a little bit in that this is far more complicated to optimize for. If you start at 0, 0, chances are that you'll find this one again. So here, I just looked at it and started close to the second point. But you can think of different, more advanced techniques to find those different points, all sorts of ways of doing that. And if I walk the events again with the speed of the satellite, I get a nice map with the hot cluster around the satellite. So I can now do the same thing, find that cluster, label those events, and I have my satellite events. Okay, so with all that, I think that we're pretty much done with the computer vision part. We've isolated the stars and the satellites, so we pretty much know where things are in our recording in pixel coordinates. Now, the problem is that nobody cares about pixel coordinates. What people want is the position of the satellite in space.
Before we get there, just a quick question. I will try to compress sensing stuff on here, because it sounds like a great problem for like the identifying the stars, right? It sounds like a great problem for computer.
I have not, and I don't think that any of my colleagues at ICNS have tried either. Because yeah, it's still fairly new, using even cameras to look at stars. There are all sorts of techniques coming from more conventional astronomy, and some of them just use, I illustrated it with connected components because that's the de facto standard technique for conventional astronomy images. But yeah, I'm sure that we can try all sorts of interesting techniques here to solve that particular problem, and hopefully in a more resilient way. Whilst we're here, I should mention that there is a notebook on the Slack with all the figures generated here. So if you want to fiddle with that or try different techniques to solve the same problem, download the notebook and have fun with it. Okay, so we want to take this data and convert it to sky coordinates, because that's what really matters. We want the physical position of the object in space, at least its direction. And for that, we need to talk a little bit about star coordinate systems. Okay, so astronomers have a system that they call right ascension and declination, or RA and DEC, which is essentially like longitude and latitude for points on Earth. So that's your usual picture. It wraps your head a little bit in that we're really inside that sphere looking outwards. So the right ascension direction is inverted compared to what you'd expect at latitude. So all sorts of little mental traps here. On top of that, you want to define the position of stars ideally in a somewhat fixed way. It's great if a given star is always at the same latitude and longitude, kind of like points on Earth. But because everything is moving in the universe, you need to find a clever way to define what's static and how you position things related to that static frame. So there's an entire research community that deals with that. The most recent and advanced way of doing that is the so-called ICRS, which is related to the center of mass of the solar system and defines very precisely how you do all that. It's worth mentioning that that defines a direction in space. You assume that everything is at infinity, which means that if you're dealing with close objects in their 3D position, like a satellite, they are so close to us that the direction of the satellite will change quite a lot depending on where you are on the planet. So this data only makes sense if you're also pairing it with your position on Earth at the time of the observation. So the frame's good. Very fast stars move very slowly. Barnard star, which is one of the fastest moving stars as far as we can tell, moves ridiculously slowly in this frame of reference, and that's great. It means that we can hard code catalogs of stars, and we can assume that they pretty much don't move at all unless you're looking at very precise things. We usually sort of ignore all sorts of nasty effects that have to do with the speed of light and the fact that if you look at a satellite, the light you're getting is actually the light from the past of that satellite. So the satellite is not actually exactly where you're seeing it and so on. But that becomes important if you're communicating with third-party systems. And that's really the whole point of this, in that if you want to sell your data to marketplaces that are interested in satellite positions, this is the most basic thing that you can provide. You can also provide more advanced constructs like the full orbit of the satellite, but the sort of step one is, can you tell us the direction of the object from your perspective? Just give us this area index stuff, your position on Earth, and the time of the observation.
Why is it, do you know why it's called right ascension? Ascension means when it ascends into the sky, right? But right means looking to the right or something?
Yes, that's because the plane of the satellite here, in a sense, crosses your equatorial plane in 2 points. And in one point, it's kind of ascending to the right, and the other, it's either ascending to the left or it's descending. So this is the point where the ecliptic crosses in the way that ascends to the right. At least that's my understanding of it.
To the right?
So if you look at this blue line, right?
The
and
right
if-
side.
Yeah, basically come down to how do I define?
Hope it survived.
So really you want to tell the difference between this point and that point. So if you look at your sphere from here, the blue line is ascending to the right. And if you were to look at the same sphere, if you think of it rotating 180 degrees, the blue line would appear to be descending towards the right.
Yeah, I don't get
Does
it.
that
Anyway,
make-
talk about it. That's so good.
Okay, so how do we do this? How do we go from our pixel coordinates to star coordinates? Fortunately, there's a lovely algorithm that can do that for us. And so there are different algorithms really that can do that, but perhaps the most convenient one is called astrometry.net, which is both the name of the algorithm and the website. And it works as such. You start with an image taken from your camera of stars, and you have no idea what those stars are. And you don't even tell it what the size of the field of view was. No information besides those stars. What the algorithm does is first extract the stars in a way that is very similar to what I presented earlier in terms of computer vision. And then it does essentially point set registration. There are a few more details about how it does that. And it will give us some sort of transformation, a matrix really that tells us how to convert from pixel coordinates to star coordinates, or if you invert it from star coordinates to pixel coordinates.
So
Now,
no matter what star picture you give it, it'll find where it's looking in the sky.
yes, it's really
As long as there's a few stars there at least.
yes, you typically need at least 5 or 6 to get
5 or
something
6
robust.
stars. With the magnitude, or does it use that?
It doesn't use it directly, but in the way it works, that's my next slide, it's better to sort the stars by magnitude.
Sort them? In what way in this picture? How do you sort them?
As in, so internally here, so after extracting the sources, it will actually generate a list of pixel coordinates in a certain order. And because it's very expensive to just treat all the stars in one go, it actually splits them into smaller batches. And it does that in order of magnitude. So you will first do a batch of, say, the 25 most bright stars in the picture, then you'll go to the 25 next ones and so on. So it's usually a good idea to try and mimic that order to get better, more robust results. So now with events, we don't really have a frame. We could generate one, but it feels a little wasteful because we've already done all that work of finding the position of the stars. So what we did is write a little Python library that wraps the original algorithm, because the implementation is open source. And that way, instead of regenerating a frame from our events, only to have that frame be extracted again, we just directly give the pixel positions that we extracted ourselves.
But does your library then do all this warping and stuff and then produce finally a picture of the stars?
It returns this transformation, and then you have to do some extra work if you want to visualize it. Sorry, okay. Okay, so there's one very important thing here. So point set registration is a family of very conventional algorithms that come down to the problem of I have 2 point clouds in 2D or 3D space, and I want to find a transformation with different rules. Can be just translation, could be translation plus scale, could be translation, scale, and skew, and so on. That turns the first point cloud into the second. Usually, those algorithms rely on structure. They are quite often designed for 3D scans, where you have 2 3D scans from 2 different perspectives, and you're trying to realign the point clouds. So each point in and of itself is not all that important. It's really the structure, the 3D structure that they form that is important. Problem is that with stars, the 3D structure is meaningless, and what matters are the individual sources. So I've tried to just use those point registration algorithms. They work terribly poorly, and none of
But I
them.
thought this is what astrometry.net does. It doesn't do the point set registration?
It implements the same ID, but not with those conventional algorithms. It has its own way of doing it.
Why don't you just use that? What's wrong with that?
If you use those, you mean astrometry.net?
Yeah.
Oh yes, I will. It's just I'm motivating the reason why they're not doing what everyone else is doing with point registration, and they have their own descriptor. And I actually find that descriptor quite brilliant. So the way it works, instead of directly working with the points, you first build an extra abstract construct that they call quads, where you pick 4 stars in your field of view semi-randomly. And because you want to be invariant to scale, translation, and rotation, because you don't have that information in your original information, what you do is you pick 2 of the stars, and they will define a little square. And then you look at the coordinates of the 2 remaining stars within that square. That gives you 4 numbers, 4 integers or floating point values that are quite neat because those values are invariant to rotation, scale, and translation.
Cool.
On top of that, they're really easy to search. You have a massive database of all sorts of quads. And from your data, you can calculate those quads and then find a match. And that can be quite fast. You can sort those and have some sort of binary tree or all sorts of clever database techniques to quickly search it. So if you look at what the database looks like, if you look at some chunk of the sky, those are all the quads that they generate. So there's a little bit of overlap. So if you want to see if your data is this part of the sky, just extract quads from your data, build a bunch of them, and then see if you can find those quads in this data.
Each quad has a different color here and they're kind of shaded. I don't know. Can you just point one of them? They look like triangles to me.
Yes.
One quad.
So in some cases, they only use one of the stars and they build triangles as well, but they still call them quads, which is confusing. But a lot of them are, yeah, for instance, that one would be a quad where 2 of those stars would be A and B, and then we have C and D, those values. So if you're lucky and you have 4 stars that happen to be in one of those quads and you calculate them, then you find it quickly. And that's actually the reason why they need to batch it, because in your original data, you will try and build as many permutations as you can to hope to find one of the quads that happens to be in the catalog. So permutations of 25 objects, big number, permutations of 50 objects, stupidly large number, anything beyond that, and it'll just take forever. So it's much faster to work with smaller batches of stars. They happen to have this construction for different scales. So the search process can be quite long, maybe up to a minute, despite pretty good implementation, to find a good match.
You give it one picture and then it takes about a minute to find where you were looking.
Yes.
I see.
If you can give it extra information, for instance, if you know the scale, or if you have a rough sense of the location, it can prune a lot of the search space and be much faster.
That's cool.
But what's the complexity of the algorithm?
It's probably an O of n squared, if not cubed. So yeah, so.
What is the motivation for using like 4 points? It feels like very heuristic, so.
It very much is. So there are competing algorithms that use only 3 instead of 4. I haven't seen 5, but it really comes down to whoever decided to implement something and make it easy to use, combined with just 20 years of research. We're like, oh, that seems to be working quite well, let's use that. So yes, there's no pure mathematical motivation.
It works for the purpose that they need it, right?
Exactly.
Yeah.
But the talk, there was some talk, I forgot who presented it, but it was connected to Cornelia's lab, right? They were talking about some graph algorithm for like matching point clouds.
Mm-hmm.
And they had like somewhat similar idea. I found it interesting where you would take like a center point of a cluster of stars, and then you would just like of points in a point cloud, you would just represent that cluster by the differences to the center
Did
point.
they have some sphere around the point? Wasn't
Yeah.
that not very, but it was saying this, anyway, it doesn't matter.
Maybe
And of course, there's also a temporal component to that, in that it was designed for static astronomy images, where you spend a lot of time taking this one gorgeous shot of a nebula. If we're thinking about a moving telescope that is really trying to capture as many satellites as possible, you could feasibly just run that once every minute, but it might be much better to optimize the thing to be updated, knowing that you're probably very close to your previous sample, or perhaps mix that with some sort of tracking algorithms if we can update it that way.
Are there any other algorithms like since 2009?
quite a lot. So there's a mixture of a few other algorithms that essentially the same idea, just like different implementation. And then we're getting very good results with the closed source algorithms that are hidden inside some of the software that we use. I don't know if they just fine-tuned the existing models or if they found a completely different way of doing it. But yeah, quite often the bottom line is that people don't care all that much about speed because they are usually taking photos. So it's like you're in a point, take a photo, that photo exposes for 10 seconds anyway, so who cares about another minute just computing to figure out where it was. So yeah, trying to do it very dynamically really changes what we need out of those algorithms.
But on that point of the time, if you try it actually, if you do it like one step at a time, like do the quads change completely or does it stay more or less? Because that would be a problem, right? If, like if every frame you get a completely different
Good point.
set of quads, right?
I don't know because we've been using it in a somewhat static way where we have contrast maximization in the loop anyway, that's also taking a minute. But yeah, feasibly, if we can fix the former, we can, it then makes more sense to try and tackle the latter.
So what do you do next then?
Okay, so thinking, all right. So this doesn't look much different, but there's actually one big step here. Now we're not in pixel coordinates, we're in star coordinates. So this is far more useful. Stars in yellow, satellite in blue, since we segmented those two objects, we might as well show them with different colors. This is great. Now we could feasibly extract the position of that satellite and figure out where it was relative to stars, and we can give that to someone else's system to tell us what satellite that was. But that's no fun, so today we'll be trying to figure out what satellite that was. And for that, we will need to look at a catalog of satellites to try and find a good match, to try and find out of all the known satellites, one that would be a good fit for our data. So if you look at a little bit of orbital dynamics, you can describe a satellite fully within a few very simplified assumptions with only 6 parameters. You can uniquely describe the orbit of an object and the position of that object on that orbit with the 6 values. Unfortunately, things are not idealized physics with just 2 dots. There are all sorts of other things that come and modify that orbit ever so subtly. 2 of those objects are the sun and the moon, but they also have gravity, not just the Earth, and they will ever so slightly impact our orbit. Atmospheric drag, turns out that the atmosphere doesn't stop at 100 kilometers or whatever border you want to set for space. It keeps going. It becomes very, very thin, but those objects are moving really, really quickly. And that drag will slowly slow down those objects and also impact those parameters. And finally, one that kind of surprised me when I first looked at that is the fact that the Earth's gravity is not uniform. The Earth has like hotspots where the gravity is slightly stronger. For a satellite moving quickly in low Earth orbit, hardly matters. But if you look at an object in geosynchronous orbit, for instance, depending on where it is, it will always see the Earth as slightly heavier or slightly lighter, and that will in turn impact its orbit. All those
has a bigger effect on geosync than near low Earth?
Yes, because if you have a low Earth object, low Earth orbit object, it will average out those effects because it's moving quickly, where the geosynchronous object is always facing the same hotspot or the same cold spot.
I see.
So what physicists did back in the 70s is perhaps your physics 101 and yet a brilliant algorithm, where they say, well, we'll assume that it's the simple case and add small nonlinearities to account for all those effects. And then build all sorts of models and sines and cosines to build what is called SGP4. It's not necessarily the best algorithm to propagate satellites, but it's become the de facto standard. It gives you pretty good results. It's really, really fast to calculate. And it also doesn't matter all that much if you have a much better algorithm, because there's a fourth effect here, which is maneuvers. Even if you're perfectly good at modeling physics, someone could still move their satellite and you have no way of knowing that. So SGP4 is usually good enough for all intents and purposes in that if the satellite has not maneuvered, it'll be precise enough for you to go and look at it and confirm they're still roughly in the same orbit. So that's one thing, but then we need those parameters, right? We need to know what those values are, the 6 parameters to describe the orbit, and those perturbations, a few extra parameters to describe how that orbit changes over time. Fortunately, the US has us covered as they release daily a catalog with all their estimations for the objects around us. It's kind of a tragedy of the commons that I'm trying to fix here, where everyone wants to hide where their own satellites are, but also it's in the interest of everyone that satellites do not collide. So the point was to say, let's release what we're doing, everyone will be using it, and that way we'll minimize the risk of losing our very, very expensive assets. Because it was designed in the 70s, it was designed to be compatible with punch cards, which is why you have those 3 lines with a very set number of digits. People are slowly moving to a more modern format, which is some sort of JSON thing with the same sort of information, but that remains the de facto standard for a lot of systems. So we take this data, give it to SGP4, and we tell it, please give me the position of the object in the future or in the past, and SGP4 will happily calculate that for us. The problem, at least in Python, it's slightly less bad in Java or other languages, is that whilst the SGP4 propagation itself is really fast, SGP4 doesn't give you the direction of your satellite with respect to your position. It doesn't know that. What it gives you is the position of the satellite in XYZ space around Earth. So you still want to somehow convert to your position, and that's very expensive, mostly because the Python libraries that we use, because they are the only ones out there, was designed for astronomy, where you really want a lot of precision, even if that costs you quite a lot of time. Here we want to propagate 30,000 objects to really quickly get a sense of which ones might be in our field of view. So instead of converting the output of SGP4 to our position, to our sort of the direction from our perspective in the sky, it's way faster to do it the other way around, where we take our direction in the sky and convert that to that XYZ space. And that way we can do very simple vector math to calculate the angle between the position of the satellite in XYZ and our position. We're sort of ignoring all sorts of subtle effects like atmospheric refraction and so on. That's fine. We still have enough precision here. And it really comes down to a dot product. So it's really, really quick to look at all those objects. So if you perform that operation and search for objects that are within a few degrees of a field of view, we find quite a few, which is pretty good news. So this is our original stars, and those red lines are the objects in the catalog that happens to be close to our field, to the center of our field of view.
So like 1, 2.
So we've got one here, one there, and then one there. I'm plotting all of them with dots, not connected lines. And because this one is moving much faster, it shows up as a dotted line, whereas the others seem connected, but really it's just because the dots are closer.
This is over a particular period of time, which is.
This is over a period of time, which is the exact duration of the recording.
Okay.
So really, we expect an object to be about the same length as the blue line, because we want to match not only position, but also the speed. And that's a pretty good match. It's not too far, because SGP4 is imperfect. It's not accounting for all the effects. There's usually a bit of drift, but that's actually the reason why we need those SSA systems, those space situational awareness systems, to find the satellites, because we need to regularly update our estimations of those orbits. So great, we could actually contribute right away. We could just give that data to the US Space Command and tell them, hey, actually, Breeze M debris is not quite where the old orbit predicted it would be. It's moved a little bit, which is pretty nice. And because this is a pretty good match, you can actually look up on the internet what exactly that Breeze M debris is. There we go. So it happens to be on a highly elliptical orbit. And the reason is that it is the upper stage of a Russian rocket that puts a Canadian satellite on geosynchronous orbit. And to do that, you would typically use the first stage of your rocket to go in a low Earth orbit. And then with a series of kicks, you would slowly raise the apogee of your orbit to get a more elliptical orbit. Once you reach that point, you would release the upper stage of your rocket and let that upper stage circularize around the Earth. And well, that object is now space debris. It's out of fuel. You cannot control it, so it's just spinning freely there. Fortunately for us, it's not the case of all the objects. This one has a relatively low perigee, so it comes back down really close to the Earth. And thus, every time it does that, it drags a little bit on the upper atmosphere. And so it's slowly coming back down. So in a matter of a few years, that object will probably re-enter the Earth somewhere. And it's quite a big thing, right? Like if you look at the object compared to a human, that's a pretty serious object, right? So that was in the sky of Telluride a few days ago, just floating overhead, which I think is kind of cool. Okay, so
But how did you get that picture?
I searched the internet for an Breeze M stage. So this is not the stage that we saw. That's a series of rockets, so that's probably another one. But yeah. And this is by no means true for all objects. Sometimes you search the name of the object and the answer is secret defense satellite, period. And that's also why people are so interested in looking at those objects, because we have very limited knowledge as to what their role really is. Okay, so what's next? What's the point of all this? We want to move all this to space. And the algorithm that I presented today was giving us decent results, are by no means efficient and not terribly spiky. So it feels like there's a good opportunity to try and convert that to more neuromorphic hardware and see if it's competitive, see if we get lower.
But just before you do that, how do you actually make money on this data? Is it possible to make money, and will the US pay you for this information?
They will, but they don't pay much. So
A few cents, or?
I think that's maybe a few dollars per observation, something along those lines. So if you're really good at making a lot of observations.
But is there an established way to feed your data? Like you tell them at this instant of time.
Yes.
This satellite was in this position with this velocity from this point on the Earth. Or,
there is.
In absolute coordinate, I guess.
Yes, there is a somewhat complicated API with a very long and windy introduction process. So you have to jump through all sorts of hoops to get access.
It has to be vetted, right?
Yeah, exactly.
You corrupt the catalog easily.
Yes, but then you can become one of the official providers. That said, what we're moving to, I think, with the AstroSite system, which is doing something very similar, is not so much data as a service, but rather the system in its entirety. In particular for governments, it's far more interesting not to buy data because it's data that everyone has access to, but actually get your own data. It means that you can look at whatever object you want to. The downside of those databases is that if you buy data for a particular object, everyone knows that you're looking at that object, that you're interested in that object. And that can cause all sorts of problems if that object happens to be from one of your allies and so on and so forth. So there seems to be quite a lot of value in owning your own systems and controlling your entire network. But that really depends on the sort of business model you're going after ultimately. It's worth mentioning that this is, of course, optical. There's also a lot of work done with radar, and radar vastly outperforms optical for low Earth orbit objects. It's much better at finding all of them really quickly, giving good estimation of trajectories and so on. Optical tends to be better when the objects are far away. And usually people will want a bit of both to cover all their bases. But yeah, I think that the world leader is still the radar company, Yulia.
Yulia is probably the world leader in terms of radar, and they operate a couple of massive, $100 billion installations around the world. And then for optical, there's a company called X Analytics, which uses conventional cameras, and they have something like 120 telescopes around the world. And if you pay them enough money, they'll point all 120 whatever you want. So, the marketplace is evolving as people decide what they want.
So yeah, the goal is to see if we can move all of this to space. So think of ways of converting those
Why would you want to move this into space when on Earth you have basically unlimited power? You're subject to the weather.
Very good question. So two reasons mostly. One of them is that daytime observations are really difficult. Yeah. But that's also the best time if you're a satellite and you want to look down. So typically the time at which you would want to know where the satellites are is the time where it's the hardest. So someone can feasibly, there are all sorts of stories of different countries maneuvering their satellites just at the right moment to fly over something where other countries thought they wouldn't fly over. So you don't have time to sort of hide your very new prototype plane or something that someone could take a photo of, that sort of stuff. So a bit of a cat and mouse game. So space gives you an extra vantage point. It's easier to see objects during the day because, well, there's not really a meaningful day. The other is a matter of location. So here, those are satellites above the ground. We are above northeastern China with the ISS. If you happen to not be Russia or China, it's going to be really hard for you to have assets on the ground that can actually see those satellites at that time. So if you're interested in some maneuver of those objects, you want to be in space at that time. But of course, space is very difficult because you have limited access to power, or perhaps more importantly, you cannot generate too much heat. You have very limited bandwidth, and you're looking at something with feasibly very high dynamic range. There might be like the sun in your field of view, and you still want to try and find satellites. So that's where we think that neuromorphic cameras have potentially a very good match for that problem. The question really is, can we also use neuromorphic computing attached to those cameras to do everything neuromorphic? And then you would beam to the ground a few bytes per second of just the estimated parameters for the orbits of those objects. So that's perhaps the fourth step here. Once you've identified the satellite, what you can do is use a Kalman filter or something similar to update your estimation of their orbit. The follow-up tech problem of mine that I'm nowhere near solving, but I think it'd be interesting, is if you assume an important assumption that we had to make to find the position of the satellite is our position on the ground. We need our latitude and longitude to know. For the ISS, we can do it pretty easily as well because there are all sorts of eyes on the ISS at all times, so we know exactly where it is. So we can also inject that in the algorithm to find our position in space and thus calculate the position of objects. But if I had, say, a small CubeSat and perhaps no easy way of calculating its exact position of the time, the problem is more complicated. I'm now only working with an estimation of my position and of my direction in space. I also have only estimations of the positions and orientations of objects that I'm looking at. And I'm not even sure which object is which, right? So I'm adding to the optimization problem an assignment problem. What I quite like is that this is essentially a constraint solving problem. And that's one thing that neuromorphic hardware is quite good at doing today. So what I'm wondering is whether we could have a non-orbit system that could feasibly solve everything at the same time for us and beam all that to the ground.
That's SLAM, right? It's a special case of.
I think that's pretty much SLAM, yes. But are we ready today to put SLAM on orbit with very efficient neuromorphic hardware? You ready?
I don't know.
I don't know either.
Well, just doing SLAM at all, I mean, by any means, I don't know why you wanna go straight to neuromorphic, except you can try to market it that way, but you know, SLAM algorithms have been developed for decades now, and they're pretty efficient, right?
True, absolutely, and
People run them on little robots and.
But there is neuromorphic SLAM, right?
There is.
And the
Like I
data
say,
is there.
But Sonny, why, first you have to rule out that you can't do it another way, right? At least you need a reference.
Yes.
Doesn't make sense to go straight and
I absolutely
make
agree.
it do it the hard way, do it the easy way first.
Yes,
Yeah.
absolutely. But no, you're absolutely right. That's it for today. Happy to take any
Yeah,
questions.
first, follow the Microsoft problem. First solve the problem and then optimize it.
I think that's a good
Right,
idea.
that's, get to market first, right? That's the important thing. Time to market is the most important.
Not that we want to follow Microsoft's design.
No, I mean, it's
No.
successful, right? First you solve the problem, like that's same Facebook, you know, Facebook internal code is just crap.
So
They
that's
have to
true,
work
but I think you're missing some points here, because I don't think you would take a conventional system right now and put it into space, right?
I mean,
That's
Why not?
People are
It has to be rad hard in some form, right?
people are readily doing that. So some people are looking at space situational awareness from orbit and so on with conventional systems. So the thing that I quite like with those problems is that we are looking at incredibly sparse scenes, and that makes at least even cameras naturally efficient in a way that is.
Just treat them like cameras and
Yeah.
just let the rest conventional for now, at least you have to set a reference.
Oh, absolutely. And that would absolutely be the first step,
Yeah.
but I'm kind of interested in step 2 as well. Can we use that as a means, as a driver to look at neuromorphic technologies and how sensing and processing interact with one another?
So what's like the biggest pain point right now? Like of all of what you've shown, like what's the first thing that you would want to get rid of?
I think that the whole astrometry.net is a big pain point at the moment. The code base is massive. The code is sort of slow because it doesn't account for the fact that it's smoothly moving. I'd love to see how we turn that into a star tracker. And that happens to be, so just this problem in and of itself is already a big sort of space application of just figuring out where stars are around you. At the moment, that's done by mostly a French company, and we were leader on that. They did buy an even camera a year and a half ago, so they are actively looking at seeing if they can use even cameras to do the same thing. But my understanding after talking with them is that they took an intern with virtually no experience in neuromorphic engineering, and they told them go look at the camera and see what you can do with it. So we'll see if they come up with anything. But yeah, there's people are moving in this direction because it seems to be a good match.
It's a little bit fake because, you know, you just, on a system which is running in continuously, you just solve the hard problem first. And then everything else is iterative after that, because you're gonna move smoothly, right? So you only need to solve the hard problem, like, you know, in MPC, you know, you have this big initial optimization step, and after that, you're very close to the right solution. So I don't understand why, you consider this a big problem if you have to do this just once, after the ISS is done up. Now you know where you're looking in space, everything else is incremental update from there.
That's actually a good point. I would say that if you I don't exactly know where that fails. I need to look into that.
Yeah.
But conventional star trackers with cameras typically stop working if your satellite is spinning at more than 1 rotation per minute, which is not all that fast.
Are you talking about being on ISS, which is not gonna spin?
I'm not talking about the ISS. The ISS has plenty of stuff to solve that problem. I'm talking about a possibly tiny CubeSat that would have to solve the same problem. And that thing can be spinning widely. And you like to know, chances are that you want to use an IMU as well, and maybe combine it with this. So I'm still fresh to exactly where the problems lie on orbit. And that's why I'm very keen to interact with people from space agencies to really understand what the challenging points are. One possible interesting way.
So let me see if I understand. So the idea would be you put the cameras up on a CubeSat. The whole purpose of that CubeSat is just to survey space junk.
Yes.
And it would just, you'd have a bunch of them, all they'd be doing is looking for space junk in different orbits. That'd be their sole job, and then they'd have to know when they see something moving against the stationary background, although it's not stationary, then they have to be able to.
Yeah, that would be a reasonable scenario, I think.
Yeah. That's it, man.
Yeah, well, you can take it one step further. So if you have a satellite that wants to take pictures of the ground, it has to figure out exactly how to point itself so they can look at the spot on the Earth. The way they do that is to look at the stars and figure out exactly where they are very accurately. So a lot of satellites will have star trackers that are there solely for pointing. And the idea is that if you can get this all to very low power, where it's not really a capital system, you could have a sense that could both do that and at the same time be looking out for any space junk that goes through.
Right, but the star tracker, which has been working now on these satellites for decades, right? They just fix on a star, a bright star that allows them to fix relative to that bright star. It's not so much about fixing, you know, knowing exactly where you're looking in space, because you can always serve on your look from the ground. You say, I want to look in this direction. You're saying that the standard star trackers are, you know, mass production.
Yeah.
From satellites, right? At least they're standard items for satellites, right?
But for CubeSats, you don't even need a star tracker because you can just do a forward orbit propagation model on the thing, so it knows where it is, and then because you can communicate typically with it every 12 hours, you can update it with where its current position.
But it still has to position itself in space, in orientation, right? It has to do that it has to be able to stabilize itself.
Yes, and they have magnetometers on board to stabilize and also 3
Oh, magnetometers, okay.
Yeah, they have those, but they also have magnetometers which dampen the rotation and take out, they use some of the Earth's magnetic.
So you're in those details, yeah, but it's complicated.
But then the other thing, for example, is if we start putting things all around the moon, that gets even more complicated because we don't have things like GPS satellites. So to figure out where you are all around the moon, actually a really difficult problem.
I don't really have any idea how they do that, yeah.
I don't think anyone does. So whenever someone says I'm going to drive a rover on the moon, you're going to say, well, you're not using GPS for that, so you have to have a whole different system.
And that's likewise where you might be able to use a high dynamic range camera, event or not, to look at the moon and also at stars and so on. So I don't know if neuromorphic is the answer, but I think that it might be. And to me, that's good enough.
Pieces of it for sure.
Yeah, I made this lecture on Star Trek because I want Star Trek memes. I think the idea is very cool. There's some stuff to do there, but I haven't done shit yet because I was busy with the Nick group. But it would be really nice guess, I mean, if people are interested in that, we'll just have a talk and sit down somewhere.
I'd love to look into moving some of this stuff to proper hardware, not just Python.
But then you have to understand the scale of the problem and the representations. the
Sure,
numbers,
algorithm
things
first,
like that, yeah.
the algorithm has to work first and then
Yeah.
the hardware.
There you go. Then make it work first and then optimize it.
But actually, totally to that point, I think there's one interesting thing, which is that Microsoft approach you talked about, hacking it until it works and then proving the concept. That works really well on the ground. It's basically the one place where the cost of extra power and extra heat is extra.
I know, I was trying to be provocative. Don't try to find some optimal solution where you don't even know what the bottleneck is, right? Find the bottleneck and then optimize that piece.
I think this basic problem is pretty much everything.
Okay.
And the biggest one is you can't just go push the reset button.
I mean, you should read the convention section, that we did for ISCAS, and when Giacomo said, I keep violating this basic rule that first you should find out what's important to solve, instead of making a solution when you don't even know if it's important.
Absolutely.
Yeah. I'm gonna share that confessions paper, so you can read all the confessions. Yeah, it's cool. Is that it then?
That is it.
Bravo. You guys know any of this stuff before? I didn't know.
Yeah, so I was gonna say that so right ascension comes from being on the equator. The sun comes up at a right angle.
Oh, that's.
Say that again.
So when you're at the equator, the sun
At the equator.
the sun comes up at a right angle. So that's
Yeah.
why that's so right ascension is that around that axis.
Okay. Oh, I see, it's right angle ascension,
Yeah.
not right.
Yes.
Not.
Oh, okay, I had that wrong. Thanks.
Okay. Let's see, thank you. That's great.
Yes.
I might have to remind to myself.
Yeah, that was wonderful. Alex. Really, wonderful tutorial on this stuff. Fantastic. Have you given that one before?
Oh, no, well,
Anyone?
yeah.
Great. You just explained
You
how to
know
do it.
everyone better
That's
than me,
wonderful. Thank
but
you.